vais tirar? Não era suposto.
Epá, isto é uma letra. Quem é que faz exames assim? Ninguém lê esta letra, por amor de Deus. Acho que é professor Pedro Lima.
Vá lá.
Bom, então, olha, eu vou dizer o telemóvel, é mais fácil. 91, exclui os 96. 4. Quem é que tem o 914? Levanta o braço.
Ainda há 3.
Quem é que é 914? Levante-se.
É o hoverboard, pá.
Só há um 914?
Pode já não estar cá também.
Ah, bolas. Chamas-te Manuel? Nunes? Pronto, aí está.
Espera. Onde é que está o Manuel?
Só deixar isso aí, posso só deixar bem.
Olha, fica aí. Pedro, fica aí. Aí é capaz de ter cadeiras. Seguras? Segura. Não segura tudo. Ah, ok. Tratar das cadeiras. Alguém que... Cadeira.
Teste?
But I can.
Maybe the machine hasn't turned on that. So, hello everyone. You can hear well, I hope. Okay, so welcome to JEEC 18. We are now going to have our opening talk. We are going to have Patrick van der Smagt. He's coming from Munich and he's the director of Artificial Intelligence Lab at Volkswagen. And the title of his talk is Simulating Time Series Data. And so he's going to talk to us about how we can use all this data that we have today to do many predictions, okay? So help me welcome Patrick, our first talk at JEEC.
Thank you, Telmo. I will try to do better with the microphone than you did. I didn't hear anything back there. Okay, I have a problem, and the problem is that this talk I'm going to give you today is based on a talk I gave last week or the week before, and it was 2 hours long. I don't have 2 hours today. And the idea was, the organizer said that I talk to you for 1 hour and then you question me for half an hour. Now, in my advantage, it is to change that you question any time you want during your talk, and then I can just talk all the time. So don't expect half an hour of question time at the end. Please do it in the middle, right? Good. There we go. You see that? Oh, you were looking at me. I'll do it again. Now, my talk is going to be about artificial intelligence. And the question here is not who is the most artificial intelligent one, but who's the most intelligent one. And let's not focus on the first two, but on the third horse and the rider. So who, please raise your hand, says that the rider is the more intelligent one in this case? Okay, I've got 2, 3. Okay, who thinks the horse is more intelligent? Okay, those 3 people, you were totally biased towards people. Okay, let me just give you a hint there. Why? I would agree that in this case the horse is more intelligent, but why is it? Why can the horse recover from this and the rider cannot? Anybody has an idea? Come on. You have ideas. All right, let's try it again. Anybody has an idea? Why is the horse more intelligent or reacting more intelligently than the rider? Yes? Its body was made to do something like that. Evolutionary, okay. Okay, it's been riding for millions of years and the horseback rider only for hundreds of years. Possible? Possible. Other reason? Yes? The horse is expecting and the rider isn't. It's almost, I would almost go with that one. And let me run you through an explanation of this. So what you see here is a muscle on the left, and you see the same muscle cut open in the right, and this green boxy over there. And this muscle has feedback through the muscle spindles. Forgetting about the Golgi tendon organs in this case, doesn't matter. And the muscle spindles, they say something about the elongation of the muscle. And if the muscle is being pulled, firing rate increases. Now what you see there in the middle, this grayish thing with the yellow and the blue, that's the spinal cord, right? So the spinal cord gets the feedback from the muscles. It's being activated, so high feedback comes, high activity feedback comes back to the spinal cord, and you have to decide something on that. Now, if you look at this one, it's similar in that aspect that the feedback, of course, because of the activation of the muscles, is also something like elongation of the muscle. You get high spiking feedback, and no elongation, you get low spiking feedback. Now, if we're looking at the human arm, the biceps, we're talking about 250,000 order of muscle fibers. And you've got maybe 10% or maybe double of that, nobody really counted, number of muscle spindles. So several tens of thousands of muscle spindles just for one muscle in the human body. It's a big muscle, but still. And you get this feedback, this high dimensional, this 25, 30, 50,000 dimensional feedback. And then you have to decide, well, how do I react to this input? As a horse, am I stumbling? Or as a cat, am I jumping? So should I relax or should I activate the muscle? Right? 25,000 dimensional factor back, and you have to do something. Now, and this is the architecture in the spinal cord that you have. So you have got there in the middle those orange things, the alpha motor neurons, and they get feedback from the 1B efferents, that's the muscle spindles in this case. And it's a quite simple circuit, right? There are like small number of neurons there, and you have to react to that. So how can you react to this 25,000 dimensional feedback signal, comparing that basically to what you were expecting, right? Because if you're expecting the impact, then you have to activate the muscle, but if you're not expecting the impact, if something went wrong, then you have to decide differently, and this simple circuitry does that. And we're talking about in the human body, you have signals coming from the brain, and those signals gate those neurons to make a decision to activate or relax the muscle. And we're talking about hundreds of thousands of muscle spindles in the body, millions of tactile efferents. Well, pixels in the eyes, it's maybe an unfair number, but it's the message being it's a very, very high dimensional number, very, very high dimensional feedback signal, and you have to do something with that. So that's why my talk is basically on dimensionality reduction. But it doesn't sound so sexy. So I called it probabilistic deep learning, but then that's too popularistic, so then I called it what it actually is, variational inference for unsupervised temporal process learning, and nobody understands a word. So it's about simulating time series data. It took me a while to get there. I'm doing this work with my group of researchers, order of 20 people, in Munich, and we focus on playing around with data to do all of that stuff, to recognize, to model time series, to make predictions of time series, and to use them in control. Talking about control. What's the horse really doing? So, anybody of you knows a PID controller? Who knows a PID controller? That's not enough, but still a few people. So this is basically a PID controller, a simplified drawing of that, where you have on your left, you have your X, and your X is your signal. If you plant, it can be a joint angle, it can be an image, it can be anything. And you're multiplying that with some constant K, or it can be a variable constant K if you want. And that gives you U, your control signal. You have to remember the X and the U. X is my data on my system, and U is my control. I'm going to use that more often. And then you put it in your plant, so that's your horse, or your cat, or your robot, or your car, or your Zeppelin, or whatever. And out comes the next measurement, xt plus 1. Again, it could be an image. It could be a joint angle of the robot. Now, and this controller is quite simple because it subtracts the feedback xt plus 1 from the desired, and that gives a delta, that gives an error, and you multiply the error with some k, and that gives you your next control signal. It's a linear controller, works very, very nicely in the case that you have a very fast feedback loop or a totally trivial system. So if you can do this fast enough, you can react in less than a millisecond to do this, then it's fine, and you hardly ever can do that. Going back to the horse, we're talking about feedback loops for the muscle spindles in the order of, I don't know for a horse. For the human, from your hand to your spinal cord and back is 20 milliseconds, 27 milliseconds. So for the horse, it's a longer distance, so maybe a bit longer. But that's not fast enough for this thing to work. So what you can do instead is you do a model predictive control, and you have, to the right there, you have a model of what the plant is doing, of what the horse is doing, a prediction. And you basically do exactly the same, but in this time you control the model over a number of steps. And you do maybe 10 steps or 100 steps in the future. And you do, again, this feedback error control in some way based on the model. But now you can adapt that in simulation, and once you have a good control, then you can use it on the real plant. Now, with this, depending on how you build your model, so under some theories of that, but you can guarantee convergence and guarantee a stable controller. But the problem is, of course, that you need to have this simulator, this model of what the environment is doing in terms of your sensory signal. So you have to predict your muscle spindle signals. You have to predict your visual input, or whatever you're measuring, your visual, your tactile input, your muscle spindle input, whatever you're measuring, in order to find what the best control signal would be to get there as efficiently as possible. So learning the simulator of the real world, or the model of the real world, is your key thing. Now the question is, how do you get the model? And let's simplify to this setting. So the ball on the right has to go in the bucket, right? And the traditional way of doing that is you measure your distance from where you're throwing to where you have to go, and then you do your Newtonian physics, and then it gets more or less right. But why does it not always go perfectly well? Because you have model errors, right? Actually, for these kind of things, it's quite simple because the ball is very heavy and the air flow influence is not so very strong. But still, in general, you can't model everything. And take this as an example. The shuttlecock movement is not as easy to predict as a ball. So you can't use your simple Newtonian physics to predict that. In fact, the movement is quite weird. It goes straight and then drops down. So it's not like a nice parabola. And predicting that kind of behavior you can't do in general. You can't predict the movement of an animal or of a human being for longer than a few milliseconds. So what you really want to do is predict the movement z of t of the shuttlecock, but you only have the x of t. Remember, x of t is the picture, is what you actually see, the pixels. Z of t, I now introduce as the real movement, like in Newtonian, the x, y, z coordinate in Cartesian space or whatever, right? Okay, so engineering model, it's very expensive to set up those engineered models. Takes a lot of time. They are expensive to compute. In many cases, it's a Newtonian thing, it's maybe not so expensive to compute. But if it's more complex things, where you need to do particle physics and things like that, it's quite expensive to compute, and in general they do not scale those models, right? They work in the lab and you go outside and your environment is different and it doesn't work so nicely anymore. So the different approach to doing this is by learning. Just go on trying and trying until you have a model that is invariant to your visual input, invariant to your muscle pain and all of that stuff. And it takes a while. Now that's basically, in my opinion, what machine learning is about. Machine learning is basically making predictions on the data that you are measuring. Chapter number 1. It's basically probability theory. The thing at the top there, Pz of x, is the key ingredient in this case. X is my measurement, right, my image, and things like that. And Z is basically a model that I want to learn of my environment that I can use to predict what's going on in the future. Now, How do you do that? And I'm sure you're familiar with these kind of things. So basically, in a very simple one-dimensional setting, you have your x on your horizontal axis, and you have a number of measurements, data, the blue spots, and the blue spots are measurements which are caused by the underlying rule, the green line, but the green line you don't know, right? You only have the blue spots. And what you want to do, you want to model this in order to be able to predict those or generate more data. So, very simple model. On the right, w times x to the power of j, and that's just a polynomial, right? And if I take m equal to 0, so this is just w0, it's just a line, and if I take m equals 1, it's a line with an inclination, and if I take m equals 3, it fits it nicely, but maybe not nicely enough, so I take m equals 9, and it fits the data quite perfectly. Maybe not exactly what we want, but it fits in the data quite perfectly. Now, linear regression is a standard way of fitting data. And why is it called linear regression? Because the problem is linear with respect to parameters. This is a more general form, whereas say my prediction y is the sum of w times some phi j of x, so some basis function. It's a summation of basis functions. The previous example, the basis functions were polynomials, but you can take Gaussian kernels, or you can take sigmoid functions, or anything you really like to do that. And the nice part of linear regression is what you can do is very easily write down a model for that, to solve that. So you say, well, this is the model I want to do, right? Y is the function that I'm using to model the data, and I have some Gaussian noise. And because I have Gaussian noise, then I can very easily write the likelihood function p of z, given my x and my w, so my data and my parameters and my noise, is just a product of Gaussians. For each data point, that's what the thing on the right says, for each data point, I want to have the maximum likelihood of this fitting into my Gaussian distribution. And I take the logarithm of the whole function, and I can very easily solve that. And what you see in the bottom right, this one in the bottom right, is your sum squared error that anybody who's done optimization knows about. And people think, well, I do sum squared error because it's a nice function I can work with. But basically, you're doing sum squared error. You optimize that because you have a Gaussian assumption in the noise in your data. What I did on the right there is plot the different polynomials, in the case you're talking about a polynomial function, that add up to the third or fourth order polynomial fit to the data you've seen before. And what you see there is this pink guy on the right. The pink guy on the right goes up to a value of 60. So it's a very unstable function because it goes up to a very high value, even for a small input value of x. It's because polynomials are not so very friendly in optimization, and numerically doing that is very painful, very costly. So what people do very often is they say, well, I have this nice linear regression, and the advantage of linear regression is that finding the parameters w is quite easy and cheap. There are ways of doing that optimally. But I know that the basis functions I have, they can get very unstable, and it's a very unstable system in general. So I'd better put my parameters w also within the parentheses. Right? And once you do that, you don't have linear regression anymore, but you have just a normal neural network. So a neural network is just an extended form of linear regression, where the parameters w that you need to find to fit your data are not just outside of your nonlinear functions phi, but also inside your nonlinear functions phi. Advantage, I've got much more expressional power. Disadvantage, finding the parameters w is now a pain because it's a nonlinear optimization problem. And I can also make it deeper. A deep neural network is just another layer of phi's and w's. This is like 2 layers of hidden units, and I can make it deeper and deeper and deeper, and I can go as far as I want or as my GPU allows me to. Any questions so far? Anybody want to leave? It's getting worse. Right, courageous bunch. Okay, so neural networks, I did my master's in neural networks, I did my PhD on neural networks, that's a very long time ago. And back then we stopped at the second level of neural networks, just 1 layer of hidden units, for the very simple reason that our computers didn't allow us to experiment that much. We didn't have the possibility to, no, let's put it differently. Optimizing one of these neural networks on a computer in the 1980s or 90s was a matter of hours and days. Right now we're talking for a small data set in seconds or minutes. And hours or days you can't wait for it and try experimenting with seconds or minutes. You can do that. So now you can make those deeper neural networks, and the nice thing, the simulation shows it very nicely, is that the deep neural network learns to create more complex and therefore more generalizing activation functions. Not activation functions, decision boundaries. The data in this case, you've got 2 simulations. The one on the lower right is a neural network with just 1 layer of 8 hidden units. And both of them try to separate the yellow from the blue dots. And of course you see that in the layer you have just a Gaussian activation function, so it's basically a decision boundary that is being given, and it's just lines, right? But if you look at the left one, the top left one, that has 3 layers of hidden units, and the first layer, the lower layer, again you see those linear decision boundaries. 1 layer higher you see more complex decision boundaries, and 1 layer higher you see more complex decision boundaries. So you're making an activation function of activation function of activation functions, and naturally that generalizes much better to unseen data than the old system did. This was just a few seconds of training, as you've seen on with TensorFlow. There you can play with TensorFlow online very easily for this kind of stuff. So these results were based on a paper by Jeff Hint in 2006, where it was shown that if you have enough computing power and if you have enough data, then you can basically train with deeper neural networks more efficiently than with the shallow ones. And that set off the new interest in these machines. Now, a very little bit of history there. I'm sure you all know about convolutional neural networks, which are very good in separating, segmenting, classifying natural images. What's very nice in this way, this is an AlexNet example. 212, I think this paper is, I'm not quite sure. What you see in the top, in the bottom right picture are the decision boundaries that are being learned, the filters that are being learned by the convolutional neural network. And what it does is it finds line filters, which you also find in biological systems. Why do you find those? Well, this basic line filter is a very natural way of finding edges in your images. We all know that from vision already for a long time. But those machines learn that for themselves. So the nice thing is that those CNNs have been beating vision benchmarks since those days and are more powerful in recognizing images than biological systems are, than humans are. We used this a few years ago also to compute optical flow. So what we did is we took a double convolutional neural network to learn the difference between 2 subsequent images and map that on the optical flow that you normally would learn with a very expensive algorithm. The nice thing, and that's typically true for these models, is that what we did is we trained those convolutional neural networks on natural images, and the natural images were extended with pictures of flying chairs. Why did we do that? Well, if you put an artificial picture on a flying chair on a natural image, then you basically know what the actual movement of the flying chair in the image is, because it's generated. So you have a ground truth, you know what the actual movement is, and then the system learns to generalize that to just natural movement in general. That works very nicely. Another example from Sergey Levine in Berkeley. What they did here is they used convolutional neural networks to predict the grasp success of a robot. So what they did is they let a robot move randomly, take the picture before the move and after the move, see if an object was grasped because of this random move, and then the CNN learns that prediction. Very nice system, very nice approach. But the disadvantage is also clear. They needed to run, I think, 16 robots, something like that, over a period of a few weeks to train quite trivial grasping behavior. It's not that very hard, but it takes a bit of a time. So that's maybe not so very useful on a day-to-day basis. Now, what happened recently as well is that neural networks were becoming common good for probability function prediction. So you don't have to just predict the value of the output, but you can also use a neural network to predict the variance of the output. And by doing that, you do two things. First of all, yes, you can predict the uncertainty of your prediction. Your system learns itself to predict the uncertainty of whatever it's predicting. But there is another very big advantage, is that now you can basically see a neural network, and I wrote it in top right, P, Y of given X. You can use a neural network to learn a probability density, a conditional probability density. Anyone. And you can also do it for recurrent neural networks. There's actually, of course, there's some...
Given this audio as input,
it's been less than a week since the deadliest mass shooting in American history.
our method produces the following output.
It's been less than a week since the deadliest mass shooting in American history. And foremost in all of our minds has been the loss and the grief felt by the people of Orlando.
Here's the ground truth video of Obama saying the same words.
Especially our friends who are lesbian, gay, bisexual, or transgender. I visited with the families of many of the victims on Thursday, and one thing I told them is that they're not alone.
To demonstrate the power of the method, we apply the same input speech mapped to 4 different target videos. Note that all 4 are synthetic and have different lighting conditions.
The auto industry, to help families refinance their homes, to invest in things like high-tech manufacturing, clean energy, and the infrastructure that creates good new jobs. Not to mention the job training that helps folks earn new skills to fill those jobs. The results are clear.
Because our approach requires only audio, we can generate a high-quality head close-up even when the original source video has low resolution or the head is occluded.
We do one Christmas trip on Small Business Saturday. I usually go out there with the girls, and the last couple of years we've gone to bookstores.
Okay.
Because the nice thing about a bookstore is you can cover a lot of ground. You can get books for, you know, the 6-year-old niece. You can get books for your mother-in-law. You know, I think we're in a moment of history where probably the most important thing we need to do.
Okay, this goes on and on. Fake porn is the more well-known application nowadays of this kind of stuff. And it's a very nice thing to do, but it's also a bit scary in a way, right? So, where are we at the moment in this history of time of neural networks? Is that we can quite well, with nice data set, good training, good computers and so on, we can separate images of cats from images of dogs. And that's important. I understand the value of that, but it's also not, I think, the end of the story. And let me explain you why not. And the rest of the talk is going to be about unsupervised learning and variational inference neural network models, and maybe Bayesian neural networks. But let me give you this test. So this is an image I stole from Josh Tenenbaum. This is a picture of things, and 3 of them I boxed for you, and let's call those tufas. It's a non-word, tufa, so don't try to associate with anything you know. That's a tufa, that's a tufa, that's a tufa. And the question for you is, can you pick out the tufa? So I'm going to give you some examples. Please raise your hand if you think that this is a tufa. Absolutely nobody. You're just scratching your head, right? Okay, good, yes. All right, who thinks this is a tufa? Few people sleeping, but most people think it's a tufa. And the last one, who thinks this is a tufa? 50-50. Okay. Now, it's not the first time I do this, and every time the results are the same. And the interesting thing, what you just did, is I didn't give you a million examples of tufas that you can learn from and extrapolate from to train your neural networks, but you did it with just 3 examples. Right? So you, as biological systems, you can, just from a very small subset of examples, you can generalize that to something that most people agree upon, at least in a probabilistic point of view. And why can you do that? Well, maybe because you recognize that has something like a foot and something like an antenna on top or something like that, or maybe a mushroom. You can name the structures, you can recognize the structures based on your previous experiences. And we can formalize that whole thing, what you are actually doing now at the moment. So I have to apologize for doing this in Portugal, because I know your beaches are nicer, but there are also beaches in Holland, and this is the one I happen to like. Please don't take that personally. Bloemendaal has a beach, and what you can do at the beach is you take a sample of the sand, and you look at the sample, and you're going to look at how many nurdles you find in there. A nurdle is a piece of plastic, right? A plastic pellet kind of thing. So let's just as a matter of argument, I'm not giving any hint here, but just as a matter of argument, you take 10 samples, and in 7 of those cases, you'll find nurdles, not just nurdles, it's sand with nurdles. And in 3 cases, you find only sand, right? To give you an idea how many nurdles, how much plastic is on the beach. I didn't do this in Bloemendaal. Take this as a message that I probably like Portuguese beaches more because you have less plastic here. All right, so question. 7 plastic, 3 sand. This is your measurement. Nurdle, sand, nurdle, nurdle, sand, nurdle, 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 sand, nurdle. What is the probability that your next sample is going to be sand? Okay, give you 3 seconds to think about that, to count 7 versus 3, total of 10. Yeah, don't spoil it for the others. What's the, so who expects the probability is 0? And you spoiled it for the others. Who expects it's 0.3? Yeah, okay. Who expects 0.38? Really nobody. A half? And nobody for a half? 0.76 and 1. Okay, good. Okay, well, congratulations. You did just this. You can formalize that. You say the P for the measurement number I. So the ith time that I take a sample of my sand. And that measurement is sand, I call that theta of I. Theta is basically my beach, right? And if you're given the theta of I for some specific I can talk about that one is a sand, right? P f of I equals f given theta of I. And you want to find theta 11, so my sample at the 11th time, by looking at what happened before. So you maximize that beast down there, and now you have to make a few assumptions, 2 assumptions. You assume firstly that your samples are independent, so the second time you get a sample is unrelated to the other samples, and secondly that all the samples are identical. So taking one piece of sand out doesn't really influence my whole beach. The beach is big enough that it doesn't get changed by that from a probabilistic point of view. So you can formalize that. Independence means I can write this complex thing out as a product of each of the independent probabilities. And the the identical, means that the i's in the p of I and theta of I disappear because they're all the same. And by doing that, the mathematics get really simple. I can just write it down for each of those, and I say theta is getting sent, right? So this is theta to the power 3 times 1 minus theta to the power 7, and it has an extremum at indeed 0.3. Problem solved. Okay? It's actually, this thing is easier to do. I showed you that before. If you just take the logarithm, then the sum gets a bit easier to do, and the maximum likelihood for the theta is the number of samples with sand divided over the number of total samples, 3 over 10, is 0.3. This is what a neural network is doing, this kind of optimization. You've seen that before, right? I've showed you that, the maximum likelihood for linear regression, and it's the same what a neural network is doing. Okay, give you a second example.
It must be the law of diminishing returns. I feel the spell about to be broken. Well, it's an even chance.
78 in a row. A new record, I imagine.
Okay. Coin flipping, 78 in a row is maybe not so likely, but it can happen. And let's take this example. Throwing a coin 10 times. First times I throw heads. Second time tail, then head, head, tail, head, 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 tail, head. 3 times tails, 7 times heads. Now, what's the probability that my next throw is going to be tail? Who's for 0? Who's for 0.3? 2 people, 3 people, 4 people. 0.38. 0.5. Almost everybody. 0.76. And 1. All right, I've given you 2 identical problems. The identical data. I just told you the one is nurdles and sand and the other is a coin. But in the first case you say 0.3, in the second case you say 0.5. How come? Could you go out, please? He's spoiling my whole lecture. I can do exactly the same slides. These are exactly the same slides as before, except that I change H's in N's and T's in H's, S's, but the other way around. So it's heads and tails, exactly the same stuff. The answer is 0.3, of course, because the only information that you have in this case is that you had three tails and 7 heads. But you're using your prior knowledge. You're using your prior knowledge. It's a coin, indeed. And most people expect coins to be fairs. Actually, they aren't. The euro coin has something like 0.56 in favor of one of both sides. I'm not going to tell you which one, because you might abuse that. Never take a bet against a euro coin. That's the message. So you have to use different mathematics, and this is the message, right? If you throw heads only twice, then it's indeed not so likely that the expectation of getting tails is 0. So you have to incorporate your prior belief, as you already said. Thank you very much. And there is a very simple way of doing that. That's Bayes' rules from do you know from when it is? 70-something? 17-something, isn't it? Whatever. And it says that, well, I can, if I have a likelihood, the PD given theta, that's the one we've been calculating so far, and I have some prior expectation, then that's related to my posterior after observing the data. That means that I'm using my prior information, I can use it mathematically directly into my calculation. The one on the right says I'm having a coin, so I expect 0.5. the P of D given theta is my measurement, 0.3, and that gives you posterior in this case. And now you can do the whole mathematics again. I'm not going to do that for you because it's just nasty, but it's not difficult. With the right prior, and there is the beta function is the prior you can use for a coin, then the maximum a posteriori likelihood equals the number of tails plus a minus 1, etc. You can read the whole thing yourself. And for the coin, A and B are both the same, they're half. And that thing then evaluates to a half if you have no data, and to the maximum likelihood if you have many data. So a mathematically very clean way of integrating prior information so that you can also work with only 1 or 2 measurements. And this is the very old discussion that goes on between frequentist statistics and Bayesian statistics. There are some people who think it's 2 camps, but it's not really 2 camps. It's just 2 different methods of counting your data. Frequentist statistics, you just count your data, you just have your observation and no further information. Whereas in Bayesian statistics, it's like a coin. You have some prior expectation of what it should be. The underlying parameters remain constant. You've seen that before. The parameters for Bayesian statistics are probability densities, whereas the data are fixed. In frequentist statistics, you need many data. You need to have so many data that it exactly describes the probability density of what you're measuring. So 10 throws of a coin might not be enough to know if the coin is fair or not. You need to do that maybe tens of thousands of times. Whereas in Bayesian statistics, if you have no data, you have your prior. If you have infinite data, then you have frequentist statistics, and anything in between is a smooth variation of the both. One is called maximum likelihood and maximum a posteriori, and the one on the left goes totally wrong if you don't have enough data. So train a neural network, which is typically a thing you do on a frequentist statistics base, maximum likelihood, with only a few hundreds of samples. Don't trust your answer. Based on statistics, if you have a Bayesian system and you have a bad prior which doesn't describe your system at all, expect a bad answer. Right? So there is no winning, it's just choosing the right model in either case. Now if we go back to linear regression, seen this one before, right? And we've seen this one. The product of the normal distributions, and we've found that the maximizing that product is minimizing that E of D, the sum of squares. And you can do exactly the same thing in the Bayesian approach by taking a Gaussian prior, for instance, on your parameters. Do the Bayes formula, you get this as a posterior, la-di-da, and then the maximum a posteriori is basically the same function. You still have the sum of squared there, plus a term alpha times w squared. Alpha is some parameter, so w squared is interesting. What this thing does is it keeps your values of w small. It is a regularization on your parameters, what comes directly out of a different way of dealing with your model, Bayesian model versus the frequentist model. Okay, now so the only thing you have to do is basically use that whole approach for neural networks, and you're done. Except that it doesn't work so well. Okay. Now, let's get back to this thing, the shuttlecock. So let's assume the only thing I have is the picture of the shuttlecock moving. And what I want to do in order to play this as efficiently as possible is I want to predict where my shuttlecock is going to be. I want to predict my future images, right? I want to predict my P of X. And I can not very easily do that by predicting each of the pixels in all the time. So I would rather have the movement of the shuttlecock and ignore the background information. I don't care what the rest is doing. I'm just interested in the movement of the shuttlecock. I call that z of t. Now there we go. I have my x, the observation, the pixel image of the shuttlecock. And I want to really represent, read the top line, I want to represent p of x. I want to represent the likelihood, the probability density of my function x. I want to predict my images. And I can write that very simply as follows. I say p of x is the integral over all my z of px given z times pz. That's just normal probability theory. That's saying nothing. But what it basically says is that my x is generated by my z. My image is generated by knowing where my shuttlecock is, the relevant part of my image. Yes, right. Now, I can do that, but remember, I can only observe my x. I can only observe the image, right? I don't know really what the Cartesian or whatever position of my shuttlecock in time is. The problem I have is how do I shape my z? How do I find the shuttlecock in time to carry the right information of x? Well, I can't. Just assume no information, a Gaussian probability density. And how do I compute this stupid integral up there? Integrals are always very nasty to compute in computers because you have to go over all the data, in this case over all the z. And since I only have observations of x, I can't go over all of these to compute that thing. So I can't really compute it. Now, the trick is that I'm not looking at z, which I don't have. I only have an observation. So I look at a specific observation x, it's a specific image, and I look in its neighborhood. Look at images close to that. Then I use p of z given x, the probability density of the shuttlecock position given my image, to sample it, and then I evaluate p of x given z there with another problem that I don't have this thing in the middle. And I don't have this thing in the middle, so I approximate it by some q, some unknown function q, and then I'm done. Why am I done? Well, it's very simple. I say I want q, my unknown function, be equal to some p, a function which I can't measure, and the KL divergent, the Kullback-Leibler divergence, is the function that computes that for me. I do the derivation, forget about that, that's why it's in gray. But I do the derivation, you come to the equation at the bottom. The equation at the bottom is repeated here. The log of p given x. P of x is the function I wanted to have, right? That's the likelihood of the image, the prediction of the image. Minus the KL divergent of q given p. Why can I have this one? Well, I'm interested in that one because I want q to be equal to p. And the KL divergent is a nice function which says if the probability densities q and p are equal, then this KL is equal to 0. So I want p of x and I want KL of q given p to be as low as possible. And that's equal to the guy on the right, the guys on the right. And the equation says I can get my generative model, my p of x. I can compute that while making sure that my q is equal to my p. And the q is the function I'm approximating. The p is the function I wanted to approximate. And that's exactly identical to the maximum likelihood of x of my image given some position of my shuttlecock minus the q, same q again, equal to some kind of prior. Take the prior to be a Gaussian function, and then the whole thing on the right I can compute, and by computing that I'm approximating the thing on the left. Right? I need that one, I need p of x. I can compute the one on the right quite simply. And now comes the fun trick. It's just a neural network. Why is it just a neural network? Well, in the bottom goes in my x, my image of the shuttlecock. I compress that to my z, which I now call a latent state, the position of my shuttlecock in something like Cartesian coordinates. And up there is a reconstruction of my x. It's exactly the function I've been showing before. And this neural network is actually known as an autoencoder, but as a variational autoencoder. And the fun thing about this neural network is that you just have to train it on images or whatever data you have, put in your x and reconstruct your x at the same time, going through the latent space set, which is a lower dimensional representation of whatever you're observing. So you're compressing this image to a very low dimensional state. It's something like a PCA, a principal component analysis, except that it's nonlinear. And the trick is that the latent space there, Q, has this Gaussian prior. I showed that in the equation on the previous page. So this is a probabilistic neural network where you just put in your data and it finds the compact representation back. To make you believe that, or even understand that, here's an example. The previous is not our work. It's published in 2013 and 14. But what we did here is we took this neural network, this variational autoencoder, and we put in data of tactile sensors. And you see 3 of those tactile sensors on the fingers of that robotic hand. And each of those gives a 22-dimensional vector. You can see a readout on the bottom left. And we just put those data into the variational autoencoder, nothing else, just the recordings. And we trained this variational autoencoder. And what you'll find, if you look at the latent space, if you look at the Z variables, we found that one of those started to represent the grip force. So it extracts the grip force from the data without being told anything about the force, or without being told anything about the physics, by just training the observations, just training the tactile data. And another of those started representing the pitch, which is, I think, this rotation. Or is it this rotation? One of those, and finger rotation. I often forget which is which. And the third one started representing the roll, the other orientation of the finger on the object. So those neurons in the latent space automatically extract those physical characteristics of what you were doing, what we were doing. Now, why does it do that? It's a bit hard to say why it does that, but I think the reason is, if you look at the mathematics of those things, is what they basically try to do is find the most compact representation of whatever data they are learning, and most compact representation usually corresponds to a physical description of a system. So that they find something that we can relate to physical characteristics like grip force and pitch and roll actually makes sense from a statistics point of view. Right. We've had the worst already. Any questions so far? I'm going on. This is just a warning. Good. Now, you can do that, of course. What is missing in this training of the variational autoencoder is temporal dependencies. So you take each measurement as an entity independent of what happened before or afterwards. And that is in general not true for things that we're observing, right? Life is not a picture, life is a video. So what we did is we took the variational autoencoder and we say, well, if you take the variational autoencoder and you train it on time measurements at time t, and then you train the same variational autoencoder measurement at time t plus 1, and t plus 2, and so on and so forth, as many steps as you like, then actually what you know is that your observation in your x space, so the subsequent pictures of your shuttlecock, they correspond to the movement of your shuttlecock, z of t, right? They're in the middle. So if I want this thing in the middle to represent the movement of my shuttlecock in something like Cartesian space or something like that, I define a filter there, and that filter is going to shape the actual physics, not really physics, but something related to physics movement of that shuttlecock by just looking at the observations. And the nice thing of this structure is that you can train that with backpropagation by just training the variational autoencoders at time t and at time t plus 1 and time t plus 2. But you can also train the system state at xt plus 1 back to the system state at xt through the filter. You can just generate gradients there. And let's skip this mathematical version of it, but show you this one. If I say my filter is a simple linear filter, a Kalman filter, then just by backpropagation I can find back my parameters A, B, and C of my Kalman filter. I don't have to hand-tune them anymore, but I can train them. So we took this as an input. It's a video of a pendulum. It's a simulated data, but it's a video of a pendulum 8 times 8 pixels, I think it is. And we trained just this observation to the system that we call deep variational base filter. And if you then look back to the latent space, this is what you'll find. It reconstructs the physics of the pendulum moving. 3 times the same picture, just colored differently. The upper left is colored by the angle of the pendulum. The lower left is colored by the angular velocity of the pendulum that is moving. So it separates the angular velocity perpendicular to the angle of the pendulum, and it finds the physics back into the latent space. Remember, it's never seen anything about the angles, never seen anything about the angular velocity. It just looks at the pictures of this thing moving. Now, mind you, this is not the physics that it's representing. Right? It's something that we can relate to the physics. But never it says there are radians or degrees or degrees per second. It's just something that we can linearly relate to what we know as the physics of the system. But still it finds that back. You can take a different transition function in the center, a different filter. So rather than a Kalman filter, you can do a dynamic motion primitive. That's simply a second order differential equation, which is very good for representing bodies, inertia changing in time. And we took tracking data of some people walking and jumping and so on. And you see the representation in the latent space, in the two-dimensional latent space on the right, that those things are very nicely represented. And if you look at the body positions that you find in latent space, is that you see that this is a very nice Gaussian representation of that, where in the middle you have the most likely position, and the further out you go, the less likely the position becomes. So it finds a compact representation of all of those body postures in the latent space. And you can then, for instance, use that to recreate movement. As you see on the right, the red is the, is that right? I think the red is the measured data and the blue is the reconstructed data. By just walking through latent space, you can reconstruct that movement. Okay, so what we've been doing is you have a very high dimensional observation, a camera image or something else. You compact to a very low dimension, like in this case to 2 dimensions, or in the previous case 3 dimensions. So 10,000 dimensional picture compressed to a three-dimensional representation. What happens if you do that compacting is that, of course, you get strange folding in your latent space. And we looked into that. Let's see, I'm stopping this video. We took an autoencoder and trained to it 10 digits 0 to 9, handwritten digits. And you see they're nicely represented, right? The blue in the top left is the 1, and the blue in the bottom is the 0, and so on. Each of them are nicely clustered into a part of the latent space and nicely separated. But what we also plotted is the distances between them. black means a very high distance. So if you look at this as a landscape, black ones are high mountains, and the light ones are flat areas. So there are some discontinuities, and usually those discontinuities are between two classes of digits. Because they are crammed together, those things have to happen. So the problem is that if you go from the green dot to the red dot, you say, I start with digit 1 and I want to go to digit number 3, and I take a straight line, look at the top right thing, you go from the 1 through the 8, through the 5, and then to the 3. It's not a very intuitive way of going from the pixel image of 1 to the pixel image of 3. So instead what we did is, well, we thought, let's not just look at this landscape, but let's also look at the first derivative of that. We can learn the first derivative, look at the values, and then do the same optimization, and you see that in the purple thing, you do the same optimization, but then take the shortest path by taking the first derivative into account. You go nicely from 1 to 3 in a very smooth way. Comparing those two again, look at the digits on the right. Because it's basically a curved space that we are representing. Now you can do the same thing for the robot arm. What we did here is we looked at going from one point on a circular movement on the robot arm to the second point in the compressed space, and you get on the right you get either the yellow, which is not a straight line in the curved space, or the purple one. And then what we thought, well, we can actually use that to realize where we do not have enough data in the latent space. Because the points where you don't have enough data in the latent space are untrained data, and that's where you have valleys. So we used exactly that to have the robot move from point A to point B, and this is a paper we submitted last week to the IROS. And it moves from one space to the other in the most straightforward way, because it's never been visiting the points in the middle. And it's fast, but it's not what you want. So what we did is we used that to train it actively to gather the data, and now it extrapolates that nicely over those objects. Good. This concludes the first part of my lecture. And that's about machine learning. Yes, a question.
How does the number of filters that you use, so the longer time steps that you consider in front of you for the variational autoencoders, how does it scale with training?
It's a very good question. So indeed, we take usually in the order of tens of steps up to 100 of steps that we can predict in the future. And it works very nicely, and we also realize it's not enough. The reason is basically the Markov assumption that we make. So the Markov assumption is that we always expect that the information we have at some time is only dependent on the information we had in the previous step. And that's not the most efficient thing you can do. And it also leads to the situation where the system forgets its behavior. So, or it's past behavior, so it's not very good in predicting. So to give you the answer, we are currently doing up to 100 steps predicting in the future of a nonlinear system, and looking in non-Markov as well to take care of that.
I see. But does it scale linearly, the time that it takes to train the network?
The time that it takes to train the network scales linearly, but it depends more on the nonlinearity of the data, so the complexity of the underlying system. We're currently using that to fly drones, for instance. There, the training takes in the order of half an hour to an hour to let them learn the dynamics of a drone based on camera images and lidar sensor data.
Thank you.
Okay. Now, in my understanding, artificial intelligence, once you've done your machine learning, if you've been able to learn your models and be able to predict the future, then using those models to make optimal decisions, and optimal is actually something that's mathematically well defined, is then artificial intelligence, right? And I think many people here know that reinforcement learning is one way of dealing with that, and there are some recent successes with respect to reinforcement learning, using those in combination with neural networks to have very powerful decision methods and powerful predictions. Here's an example. Training Mojoko. And this is all just trained on reinforcement learning, starting with basically no prior knowledge. And it's very impressive that it can do that. But the training took 6,400 CPU hours. So if you just do one CPU, it's almost a year. And that's one of the major problems of reinforcement learning. Whereas if you compare that to a fast feedback model-based predictive control, you can also get this kind of behavior, right? So you have to, yes, you have to put in some model knowledge, but if you can do that, why shouldn't you do that? And it's very similar behavior, just based on parameterized models. Okay, that's one of the problems in reinforcement learning, is that you need very, very extensive, long-lasting training. A second problem is that reinforcement learning is based on optimizing a cost function. Where's the video? There you go. So how do you define a cost function for reinforcement learning to solve a certain problem? And you can often define it in a cost function that gives you just a reward once the task is finished, but it trains much faster if you have rewards in the middle. So in this case, the idea is to put a red brick on the blue, but that took too long to learn. So what they did instead is they put a height reference as an extra reward for the system, and it's learned to turn around the bricks, the red bricks, because then the measured height is very high. Because it's turned upside down. So you have these kind of problems. It's very fragile to starting conditions. So this is also reward after 2 million iterations of the half cheetah, and depending on just the initial conditions, just a random seed of your computer, you can get totally different behavior. So it's not very stable to that. That's a big problem. And any of the papers you read in reinforcement learning, you must be expecting that the results you find are sometimes a bit nicer than they are when you run it on your own machine. Another example on cost function, it's hard to find the cost function in this one. So this is the boat racing, and you get points for winning the race. But you can also, what the authors did is to improve that, is they put points on reaching the intermediate stations. So in order to collect those points, the system just learns to run around, collect points and points and points, much more than it gets by just finishing the race. All right, so two problems: train slowly, and finding a reward function is very hard, apart from the fact that it's not very stable in its training. So we looked into the last problem of finding reward functions. In order to do that, we looked at some semi-autonomous systems and see what they do. And this is really weird behavior, because it optimizes that function, and it doesn't even like to do that. Right? It's no fun getting on your knees, but it still does it. It's not that it sees it from others, right? The brothers and the parents don't do that, but he's just standing on his knees. And why does it do that? Well, there is this nice theory going back to Erwin Schrödinger in the 1940s. He wrote a book called Meaning of Life, I think, something like that. And he called it negantropy. And it's basically the channel capacity. The problem of this thing is, if you look at the equation, I will give you nicer on the next slide, is the double integral. And a double integral means I have to integrate over all the actions and over all the states in my system, and you can't compute integrals in real time on a computer. So this thing is called empowerment, and empowerment is the channel capacity between an action and the following state. And it's defined like this, and I will make it clear to you, or will try to make it clear to you in a second. It's basically KL difference, la-di-da, la-di-da, and there's this totally terrible equation there. What it says there, if you take a few minutes looking at it, I'm not giving you that, but if you take a few minutes looking at it, what it says is that my system, according to this equation, is in an optimal state once this state allows me to reach any future state as quickly as possible. So I have maximum control over my environment, over my sensory states, basically. And it means that if I'm lying in a corner, it takes a lot of effort to go somewhere. Whereas if I'm standing in the middle of the room, I can reach every point in the room as quickly as possible. Now this function computes that, and on the bottom right, what is drawn is the empowerment for a pendulum. The one axis is the joint angle, the other axis is the joint angle velocity. And in the middle, 0, 0, is where the angle stands like, the pendulum stands like this. It's a highly empowered state, because from here I can reach every other state as quickly as possible. Whereas if I'm hanging down there at angle 2 pi, at angle pi, I have a low empowerment. Also, if I'm at the side at a high speed, then still I can reach every other state quickly. That's why I have this red area over there. Now, as I said, the problem is that this thing is intractable. You can't compute it in real time, because it's P of Z prime given Z, and that is the likelihood of the next sensor state given the current sensor state, so going from one step to the next, for all possible actions that I could make in that state. And I can't compute that, because I can't compute for every Z what happens if I put every action there. It just takes too long. So what we did the same trick as you've seen before with the variational autoencoder. We computed a lower bound, and we say, well, this I is larger than the thing in the middle. Let's not go through there. I've tortured you enough. But the error that I'm making in my approximation is the KL divergence of P given Q, and that is the plan of my movement. So if I'm planning my movement according to if I'm approximating the plan of my movement in the future, and this computation, blah, 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 I don't want this slide, I want this slide. What we did in this case is we learned for each of these balls the empowerment. Each ball is an independent entity. It has 40 LiDAR sensors. And those LiDAR sensors give it just a distance to the other balls and the ball. We've trained them with DVBF to learn their dynamics. And then we learned them to optimize their empowerment. And it goes like this. Train the system with DVBF. We have the latent space. And in the latent space, we predict the empowerment of the next 100 steps, as in model-based control. And over those next 100 steps, we take then the next step that brings us the best empowerment of the next 100 steps total. And then we take one step, and then we do it again. We dream the next 100 steps that go on, and we take the most efficient one, and so on and so forth. And so we control each of those. Each of them is independently controlled, so they don't know anything about the others, except for, of course, what they're measuring with their LiDAR sensors. We can do exactly the same for the two-legged hopper, walker. So again, we train the dynamics of the system with DVBF. Let it explore for a few hundred steps. We train the system for approximately 1 hour. And then we do the maximization of the empowerment. And what it starts doing is just standing, because standing is a more empowered action than lying on your side or on your back. Right? So both cases, the balls and the two-legged robot, they have exactly the same software, except for different dimensionalities of the data, of course. Exactly the same control law, and you get this kind of behavior. Okay, now that's nice. It gives you a chance to be in a state that allows you to be more efficiently in your future state, so it empowers you to do more in the future, but still there is no goal in this case. It seems to be working. It's really not working in this case. It's just more or less random. It's noise in the system. It's really only standing and moving a bit in any direction, basically. So what we still have to do is combine that with goal-directed optimal control, and so we have to combine that with other cost functions, reinforcement learning, to get this kind of behavior. Also here, of course, the cost function that you can find is difficult. The one on the bottom is probably, it's a better intermediate goal, but the one on the top is more difficult to reach. All right. So that's basically all I wanted to say. Let me summarize with how my group at Volkswagen works. I have a basic research group on probabilistic deep learning and control, where we use probability theory, as you've seen, variational inference for time series and deep learning. We're actually trying to surpass deep learning with quantum computing, and not very successful yet there, and combine it with optimal control and reinforcement learning to play around with those things. We do it with our robots, and our output is publications, open source software, and exchange with other people inside of Volkswagen, but just as well outside of Volkswagen. And then there is a group of applied AI people who apply these methodologies, but also other methodologies on use cases within Volkswagen with all of the 13 Volkswagen brands that exist nowadays. Thank you very much.
So, any last questions before we can have the draw? No? Oh, okay.
Yes, there's one here.
Yeah.
Yeah, I'm not sure it's a question, but so as a recipe for what I got from here is basically your suggestion is, in terms of application, is first to use the autoencoder, then leverage on the autoencoder to explore the space and get more data to get the system to know what it can do, then go to empowerment and to a center in the space where the system can go everywhere, and then use the reinforcement learning to make the system do what we want to. It's very
yeah, I know
it's a big simplification.
It's a bit of a painful question, because you're more or less true, but I left a few gaps. I left out the exploration. So the empowerment doesn't do the exploration, right? It finds a cost function, or it defines a cost function that is general enough to put the system in an optimal state, but it does not do the exploration that you need to do to learn the dynamics of your system. So that must be added, and that's indeed something we are looking on how to do that. I showed you the very short example of the robot exploring, and that's just one way of doing that, but probably not the best way of doing that. So exploration is a key pain point that needs to be solved. Two people working on that in my lab. And the second thing, what you said, is the combination of the goal state, the goal cost function, with your empowerment cost function. That's indeed something we are currently also working on. So what you can do is quite simply is say, well, I take my empowerment as one cost function, I take the other one as a second cost function, and I have some optimal way of combining the two. Works, and it's inefficient. That's the way actually we're doing right now. The reason it's inefficient is that your empowerment value depends on what state you want to reach, right? Because if you know what you want to reach next state, and getting there, then you know what's the best state before that to get there. So the two interplay. And that's a bitch. So that's really nasty. We don't know how to deal with that from a mathematical point of view at this moment. I mean, you can write on the mathematics, but you can't do it efficiently yet. So indeed, what we're doing right now is combining cost functions, target directed cost functions with empowerment cost function. Actually, we do that. We are building up a demo where we combine the drones with the robots to share the same space and have the robots do a task, and the drones interrupt them and so on, and to explore all of these things in more complex data settings. But it's both of those are major headaches we are fighting right now. But in general, yes, you're right, you have to learn the dynamics. To do that, you have to do exploration. And once you do that, you can use empowerment to put your system in a good state, and then add to that a cost function to reach your final goal, and that seems to be a more efficient way of dealing with that. Talking, for instance, about, it's a silly example, but it's about a pendulum stabilization. With those methods, we can do it in about 100 iterations, where reinforcement takes about 10,000 iterations. So it seems to be more efficient. I don't know how it scales yet.
Thank you.
Welcome.
So to finish, we'll now make the draw of the prize.
Hmm?
May I use your computer?
You can use my computer. Depends on what you want to do with it. Oh, I even have internet, yes. So a computer is really a bad way of creating random numbers, I must say that.
So
that's why we do quantum computing.
Who has the number 38? Anyone? Yeah. Thank you all for joining us, and we'll have a talk next. Will be John Viega talking about robotics. Thank you very much.
We would like to invite everybody to stay for the talk of John Viega. It's going the theme of the talk is going to be how to build a rocket ship, and we would like you to join. Thank you. think the dinner. Yeah, I thought so, but it's not always nice to ask. So thank you very much for coming.
I saw people freaking out.
Really?
Yes.
That's my case. Okay. I found your presentation very interesting for me because I'm doing my master's in finance and I'm exploiting systems and variables about for anomaly detection. I use the and just this morning I was implementing variation. With
different data variables you can do that.
Yes, and I'm using also fencing data, so I do the recurrent layers in the variation autoencoder to exploit product. So I found it to be very interesting for me. Thank you.
Thank you. Good luck.
And your group of research as like interns, like
Yes.
for the summer?
Yes.
There are applications for it, or?
We always have interns and things like that, people like that, yes.
Yeah, because I found it really interesting and I wanted to work on this area.
Mm-hmm.
So in the website, there's anything, or?
Just send an email.
Okay, send it to you? Okay, okay, thank you.
Yes.
Thank you very much.
You're welcome.
Thank you.
Question? I was wondering, what did you study before going to the big deal?
Okay, let me before I answer the question, let me tell you that if you study some of the relevant mathematics, like calculus, linear algebra, and you know your probability theory, and you can do some programming, and then it doesn't matter what you study.
I know. I was
Okay.
curious. I was curious.
So, I studied computer science and mathematics.
Okay. That's interesting.
In Germany?
No.
Amsterdam.
But it's not so relevant at certain points. It becomes totally quite irrelevant.
Yeah, I've been realizing that over the years, you know.
Yeah.
Okay.
Yeah, but so I'm not a big friend of those specialized studies in like, if they're too specialized on a certain thing, I don't like that too much because it becomes too irrelevant.
Me neither.
You need the
I
basis.
like to have my horizons broad.
Yeah.
You know?
What I actually did looking back is like change my focus every 5 to 10 years. It's not
biotechnology.
Yeah, so I did a lot of not biotechnology but biomechanics. I did a lot of brain-machine interfaces.
Yeah.
I did.
So you entered very much in control, in the area of control.
Yeah,
and
increasingly now.
precision,
Yeah, increasingly now. But that's like the last 5 years. And that comes because at a certain point you realize you need it. So I didn't know anything about optimal control 5 years ago.
Oh, really?
Yeah.
And then?
Yeah, but then it becomes necessary and interesting, and suddenly you find this whole thing, and it's fascinating. I mean, I never used reinforcement learning until last year. So
many information available, so you
can. You've got all the basics.
Yeah, you've got the basics, so it's easy to get in something which is similar.
And you
use neuroscience as a thing.
POM-DPs.
I have a paper of POM-DPs, but that was because a PhD student of mine did that a few years ago. But we don't use POM-DPs.
Yeah.
So I'm not a big fan of reinforcement learning, I must say, because it's so inefficient.
Yeah.
And it does great stuff, but it's so much parameter tweaking and.
So why is it used like? It's still used, yeah.
There's nothing else you can do really. So, but that's why we do model predictive control.
Okay.
Learn the model and then use some other way of optimal control. So what we actually can do, the trick is that with those latent variable models I showed, where you have this filter in the latent space, if you make this a linear filter, linear system.
Linear.
You
always want to linearize.
Yeah, you can do optimal control.
Yeah.
You can do it. You can just compute it. You can write down. You can just compute it. There you go. It's of course only for a short horizon, like if you have.
Yeah, it doesn't generalize that.
So it's not optimal control. Yeah. But it's optimal enough. In some cases. So it's
I
much cheaper.
didn't know that there was like a in your PCA.
There is. There is. This is what I call.
Okay. So here today we have a very special guest, which is John Viega, which is by my side here. He's the next CTO of McAfee. You may know it's a very famous company. And now he's here to talk about his career and about his job at Capsulate, which is where he works today. So let's give it for John Viega.
Thank you, everybody. I really wanted to talk to you today about inspiration. The title of the talk is Building a Rocket Ship. The real goal for the talk is to help put everybody here on the path to a successful career. I want you to be fulfilled in your careers. I care a lot about that. And I think to really understand how to get a fulfilling career, so what I'm going to do is do that by talking about my career. And I like talking about myself. I think most people do. But it will really be to tell you the lessons that I've learned that'll hopefully help you with your career. So I definitely have been on a rocket ship ride my whole career. I was successful right away, and a lot of it was luck, but there are a lot of things that you can do to make yourself more successful. And as a bonus, at the end, I'm going to teach you the biggest secret to building successful products, software products anyway. And I'm not lying about that. I'm going to teach you a secret that almost nobody else knows. So you should start with your goals. I think that in order to have a fulfilling career, it's important to know what you think would fulfill you. And that could be in your first job out of college, what do you want to learn? What are the skills you want to build? What do you want to be when you grow up? And I think that when people think too far out, most people in the tech field think the same thing. Their career goals look like this. They're swimming in money. And that's definitely possible in our field, and there's nothing wrong with that. My goal was a little bit more mundane. It was to make as big of a difference as possible. And I just think that I wanted to have an impact on the world. It probably started out really selfish, my big ego. I like talking about myself. But it kind of evolved into kind of helping the world. And I was never going to make as big of a difference as my undergraduate advisor. He is on billboards. Randy Pausch, he was my undergraduate advisor at the University of Virginia. He made a much bigger difference than I will ever make in this world. Not really because of his academic research, but because when he was dying of pancreatic cancer, he gave a very famous lecture that's been seen on YouTube 20 million times or so. He was on Oprah Winfrey, the next president of the United States, and then a book that made the New York Times bestseller. Randy was a very motivating guy in life and in death. The book, I highly recommend it. There are a lot of great lessons to help you in life. The book is about living your best life. And, some of his words of wisdom up there. One of my favorites is deciding whether you're going to be a Tigger or an Eeyore. I don't know if you have Winnie the Pooh here, but Eeyore is the donkey, and he's very sad and depressed. Tigger likes to bounce. He's always happy. He's always cheerful. He's got a positive outlook on life. Tiggers tend to do better in life, and that doesn't mean you have to jump around stage or always be happy. What it means, I think from a practical perspective for your careers, what tends to happen in the world is things happen you don't like, and you're going to complain to your friends about them. And that's a really kind of Eeyore activity. A Tigger activity is to take the initiative to figure out how to help fix them. People appreciate that. You will feel better if you get the world to a better place, and you become a better person if you're not kind of always complaining about other people. So you should listen to Randy and decide, are you a Tigger or are you an Eeyore? Now, Randy was doing some really cool stuff, and this was in 1995 when I was in college, so yes, I am pretty old. We were doing virtual reality. So I'll show you in a minute, but essentially you would be standing under some goggles, except they weighed about as much as I do right now, and so we had a support to kind of offset the weight a little bit, and you would see Star Wars. So it looks like this little droid is shooting at you, and you're holding a flashlight, but in virtual reality it looks like a lightsaber, and you're essentially fighting against this droid. Alice is still available, by the way. People still use it, but is just kind of 3D computer graphics. It was really cool. It made me not very popular. So Randy was a very prominent researcher, computer graphics, but mainly focused on how to make virtual reality easier to use. And so this on the left was a demo that I and people in the research group were supposed to build for SIGGRAPH in 1995 or 96. SIGGRAPH was at the end of the summer. It was also the summer that Quake came out. So instead of working, everybody in the lab was playing Quake all summer. And Randy was off, like, visiting another university. He was not around. So he came back about a month before the conference and said, show me what you got. And we had absolutely nothing. But I'd gotten really good at Quake, I must say. So obviously he read us the riot act, meaning he was very disappointed. He didn't even really yell. Everybody just knew that we let him down. And he said some things that I thought about, and it occurred to me that I had come into this because I was brand new to programming, and if I was going to be great at programming, I'd actually have to do a lot of it, and playing video games was not going to get me the experience to be the best. And I wanted to be the best so I could make a difference in the world. So lesson number one is, if your career goals are actually important to you, then you should be working really hard. That doesn't mean you don't have a personal life. It just means you should be working harder than pretty much everybody else around you if you really want to achieve your goals. There's no substitute for hard work. Luck can help sometimes, but really work is the number one indicator of success. So we actually got the work done by never sleeping, and this is a picture of us, what it looked like if you were at the conference. You would go under this head-mounted display. It was only about 10 pounds. And you'd hold the flashlight, and what's on the screen in the back is what people were seeing under the head-mounted display. They could fight. It was pretty great. Here's the entire team. Can you find me in the picture? Am I like one of the handsome guys in the upper left? No, I'm that guy. Oof, man. All right. So I learned to work really hard. However, I was supposed to be working on computer graphics, and after that summer, I got really distracted. I was building multiplayer online games with a bunch of people over the internet. That's actually how I started programming in the first place. I ended up, my town had a band called the Dave Matthews Band, and I somehow got roped into building them a mailing list manager, which became very popular open source software. And then I tried building them kind of an e-commerce management. It was a huge failure. So, but all of that was distracting me from actually doing work, and Randy was not very happy about it. So he took me into his office and he said, John, you're like a rocket with no fins. You got a lot of potential, but without those fins, you know what's going to happen to you? That's what's going to happen to you. If you don't have focus, you're not going to succeed. Turned out that he was wrong on a couple of counts. First, that's an actual rocket with no fins. It is possible to fly one around and have it not explode. But the advice is generally sound. Focus is really important, but my goals weren't just to produce the best possible research. I wanted to have a good basis, and I'd only started programming, and I saw it as I needed to get a lot of experience in a lot of different things. So he was really disappointed until one day I walked in and with an idea that got me my first academic paper in 1996, which was, a huge success. He was very proud, and that was that. And what I learned there is he was right. If you're a rocket, it's better if you have fins. You want to be focused on your goal. Take that energy and apply it to your goals, but don't just bang your head against the wall. You want to work smart about it. You want to be focused on what's going to help you win. All right, so after my undergrad, Randy helped me get into NYU, where they did computer graphics, except I kind of decided the summer before grad school, I don't really like computer graphics. As a matter of fact, it was boring. Like math, I was good at it, but I hated it. It was just like boring as heck, and I was starting to slack off on the math stuff because I just didn't want to do it. And this lesson, I think most people hopefully can relate to, but you got to find something that you're really excited about. Otherwise, you're not going to be the best at it. I mean, you might be really good naturally, but if you really want to succeed, you got to find something you're passionate about that other people care about too. But if you are looking at jobs out of college and you think, it'll pay me a lot of money, then you're probably not going to be great at it, and you should focus on finding something that you're really excited by. And so I thought I really pissed off the people at NYU because I left and I didn't go at all. I ended up staying at UVA because I was really interested in compilers, believe it or not. And so I did that, and surprisingly, I ended up teaching at NYU about 15 years later. So after grad school, though, I kind of lucked into security. I took a job that was pretty random. It was close to my parents. It was doing academic research. I wasn't really ready to go into the real world yet. I didn't like what I'd seen about the culture at the consulting companies or Microsoft. Like, I looked at a bunch of places and I thought, I think I might be bored, and I like kind of being able to drive my own research. And I got to do that, and at this company, I ended up raising millions of dollars in research grants through DARPA and NIST, which is the big university research funding in the U.S., and ended up doing a lot of high-profile security consulting for companies like Visa and Symantec. This is back in 1998, when no one really cared about security at all. I'm not sure people care about security today. I'm not even sure I care about security today, but definitely nobody cared about it in 1998. And but a couple of people were starting to, and that allowed me to, and the company that I went to had people who had written books, and so that allowed me to write the first book for developers on security, which was my rocket ship. It was made it possible for me to do absolutely anything. Now, I was having a good time with the work that I was doing. I liked the research projects that I got funded. I had hired some great people that were incredibly brilliant, and they enjoyed what they were doing. But That doesn't mean that I was a very good employee back then. I was very arrogant. I probably still am, but everybody knew that I was arrogant back then. And I thought I knew better than everybody else. I wasn't afraid to tell people when I thought they were stupid. And so I don't think I was very popular at this company, except for the people that worked with me who liked me a lot. Now, one of the founders who hired me in, his name is Jeff, still a very good friend of mine, and he traveled a lot. He wasn't really my direct manager, but you know, he ended up writing a piece about me in an IEEE magazine called "The Pitfalls of Managing a Superstar." And I'm going to zoom in on the case in point here so you can see how horrible I was. Yeah. I didn't want to be a cog in the wheel. So that basically said, I didn't really care about your stupid company at all. I just wanted to be big and important. And so that kind of arrogance did not really serve me well. He didn't name me in this article. He told me about it like 15 years later. I thought it was really funny, actually. So I think this is great. But you know, the experience did change me. I learned pretty soon after that even if when I thought I was the smartest guy in the room, which I often did, I had a lot to learn. And I might know the most about this part of security, but a lot of people know more than me, and I always should be learning from them. And that also means that I think it helps to not let your arrogance show day to day. Be humble, be respectful, assume that everybody's doing the same thing. They're at least as smart as you, just in different ways. So, you know, I think that there are a lot of people that are great technologists, and they can have great things to say in business too, even though business is not on their resume. And so you should listen to them and hear them out, and vice versa. So this one kind of boils down to don't be a jerk. So after that, I went out and leveraged kind of the success of the book. I was getting a lot of companies that wanted me to consult on the security of their software. So I started out a company around it, but I also knew that I had no business sense whatsoever. And by the way, so this was 2001, 17 years ago, which I think was the last time I wore a tie. I usually just wear a t-shirt. My wife made me put on a shirt today. By that time I was kind of self-aware enough to know I might be a good technologist, but maybe I was an idiot when it came to business. And I wanted to learn it, but I was okay being an idiot. So I tried to find somebody who was a good CEO. He stole money from the company, so we got rid of him. I found somebody who looked a lot more credible. He'd raised money from a venture capitalist before, and he had a lot of connections. We talked to tons and tons of venture capitalists, and you know, it didn't really pan out. So I'll tell you that story in a minute, but what I learned during the process, the first thing I learned was we started out a consulting company, but really what we wanted to do was build a product that everybody would buy to help make the security of their software better. And I could build the technology that would do that. It was stuff that started when I was doing compilers before I even knew what security was. The challenge, though, to doing that is you can't really build a product when you're doing something else. And it's not just that it was professional services, it's just that takes up too much time and attention. Keeping the company alive to go off and build a product. A lot of people tried, we weren't getting the job done. And so this guy, this second CEO I brought in thought, okay, well, we'll stop doing all the services bits and work with venture capitalists to fund us like a traditional product company. You make no money for a really long time while you're building the product, and then a rocket ship, and everybody buys it, and you sell for hundreds of millions of dollars, and you're bathing in money. So it took a long time to raise money, though, and in the meantime, we started running out of money, and it eventually occurred to me, because a lot of these venture capitalists were spending a lot of time with me. They were asking me to look at other companies for them that they would then fund, and they're still not funding me. I'm thinking, why is this? And so I asked one of them, and he said, oh yeah, we don't like your CEO. He's a liar. Everybody knows it. You'll never get funding while he's the CEO. I thought, well, that sucks. And so we fired CEO number 2, and very quickly thereafter, I raised money by myself from Charles River Ventures, which used to be one of the top 10 VC firms. Now they're probably top 20. And they and I both knew that I really didn't know what I was doing, so they made me go hire CEO number 3. Now, what I learned from taking a few years to raise money is that it really helps to surround yourself with winners, people that know what they're doing and the jobs they're doing. Even today, I probably would have been, if that company were starting today, people would be okay with me as a CEO, as long as I could attract people who knew how to do their jobs really, really well, because I could get them behind the vision of what we're doing. So I could go out and hire a great head of sales, a great head of marketing, a great head of engineering, whatever. As long as I could get those things done, then I'd be a good CEO today, even if I were 19 years old just out of college. It's about surrounding yourself with winners. They say venture capitalists invest in teams. That is absolutely true. That's a huge criteria. They are trying to make sure that the company has the best chance possible to win. And that's not just true in the startup world. In anything you do, you're going to be more successful if you find the people that are also really good and really motivated to win, and find a way to work together with them to move the ball forward a lot more. Great. So that company exploded, though. It really didn't go anywhere. The CEO number 3 was a great guy who had only worked at big companies, and he just kind of started going after very large deals, and a upstart competitor came in and was doing a lot of very small deals and started eating our lunch, and I got really, really depressed about it. They sucked too. Technically, they were doing nothing, and we had a pretty awesome product. And that is when I learned, my friends, that technology almost doesn't matter. The best technology not only doesn't always win, I would say it often doesn't win. It maybe even usually doesn't win. It's an accident if the best technology wins. More on that later. But the other thing that I learned is that when you're at work, no matter how depressed you are, no matter how much you hate your job and how much it sucks, when you're at work, you got to put the company first. You should always, of course, when you're not at work, you come first, and if your job sucks, then you should leave it, but leave it respectfully. But you really want to treat the company with respect and always be treating them first, even until you walk out the door. Otherwise, you won't have the respect of the people that you left. And technology is a pretty small community. Word gets around, and people have a very long memory. So if I had not kind of done my best for the company before leaving, and I quit when I saw that I thought the rocket ship was going to explode, if I hadn't been respectful to the people, none of those people would have worked for me again. Some people that were at that company have worked for me like 4 different times in their career. Every place I go, they eventually want to come too. And similarly, the venture capital world, if I had just said, this place sucks, I'm out of here, I probably never would have raised more money from venture capitalists ever again. So again, it's important to put the company first, but I was really depressed, and I focused a lot of my energy, though, into side projects. And you know, there's no real lesson here. I kept writing books. Oh, the lesson is don't write books. I mean, I think the first one was a tremendous amount of work and helped. I don't think that it really matters anymore. There are too many books from too many people and nobody reads them. At the time, the first one helped. The rest of them were just because I loved teaching and were just way too much work. But you know, I don't really recommend it. The second thing I did as a side project was a bunch of cryptography projects, and the biggest one was something called GCM. And I don't need to go into details about what it is, but at the highest level, it's a mode of encryption for AES that allows kind of high-speed, parallelized, internet-scale encryption, and it's in everybody's browser today. It encrypts about 3/4 of the encrypted traffic on the internet today, and at some point along the way, Intel added an instruction just to accelerate GCM. So proving that I'm an arrogant jerk, I have my own instruction on the x86 architecture, which was probably the highlight of my career. Had nothing to do with making money. It was all free. But there is really a lesson in the GCM thing. I was interested in a side project as a side project, and I found it because friends of mine, and actually somebody I didn't know, had seen some of the other work I did and said, hey, could you help us out? They were at a big company called Cisco and said, we really want to solve this problem. What you did was a good first step, but here are all the reasons why it's not going to work in practice. So it was a huge opportunity for me to learn what would work in practice, and then we built something cool. But a paper isn't going to get adopted by millions of people, be in millions and millions of browsers around the world. What did it take? It took hundreds and hundreds of people appreciating what we were doing and working with us to push it into standards, to push it into companies, and it's the same with anything you do. You can build something cool, and if you're the only one who's ever actively promoting it, it's not going to be very big. So, you know, the lesson here is that big success always requires a lot of cooperation, and that means you got to find how to align people's interests together. All right, so I did end up quitting my startup before they fully cratered because I got a great job from McAfee, and McAfee at the time was probably the coolest name in security. They had built some really great products. They really knew how to build products well. They had definitely been a rocket ship at some point, but that rocket ship had leveled out. And nowadays, you know, that was 2005. I left about 8 years ago, and at that time, the rocket was starting to stall. And recently, they changed their logo, and right there, you can see the rocket is plummeting towards the ground. And I think that eventually McAfee will explode. But I'm going to talk about 3 things that I did at McAfee. So I was hired in by the worldwide CTO, Christopher Bolin, and I started out owning the core technology and a couple other things. I'll talk about the core technology first. one of its biggest assets, definitely the biggest asset, was antivirus. It had lots of consumers, it had lots of enterprises using it, and it was widely regarded as a piece of garbage. It was not very good. When I showed up, we were next to last in terms of rankings, and for a little while I got us to next to the top, but what I learned is that it is really, really difficult to move fast in a big company because there are a lot of people there, and any decision you make, anything that you want to do, is going to have people that are naturally defensive. We all, most people don't naturally love change, and so when you're coming in saying, we have to do things really differently in order to win in a big company, there's always going to be a lot of pushback on that. And so it was really, really hard, especially because big companies, often the rocket ship is kind of stalled and they're no longer kind of dumping as much money as possible into growth. They're now focused on making big profits. And that means if you want to kind of restart the rocket ship and kind of get really good again, it's really hard to convince business folks that they should spend money, unless it happens to be an acquisition. And, you know, so the lesson here is that big companies really mostly can't innovate. There are occasional exceptions, but there are good economic reasons why they're not going to be able to keep up with startups 99% of the time, which is why they end up acquiring a lot of startups. So for the antivirus business, I kind of knew what we should go off and do, but there was no way, even though I theoretically owned the engineering and building the core technology, there was no way I could get the rest of the business to kind of get behind what I really wanted to do unless we acquired something that would make it better. So I found a company in the UK that was pretty awesome for 2007. They were essentially, at most antivirus companies, McAfee included, there were so many pieces of malware coming out a year that we were really struggling to keep up with it all and failing badly. And we try to do things like generically figure things out, but we couldn't even breathe. It took all our resources to try to keep up, and it made it really hard to innovate a better solution. Meanwhile, these people in the UK had kind of semi-automated the data science at a massive scale. And certainly the data science has gotten a lot better in the past 10 years, but they were doing a great, great job, and it would have been a huge game changer, except we did not get the deal done. By the way, this company, Prevex, was making essentially no money. The CEO was funding it himself. He had built an online dating site that he sold for a lot of money, and so he didn't really need the money. It was a labor of love for him. He built this great technology, and he was probably making less than €1 million a year at the time, way less actually. And so McAfee was willing to pay, you know, tens of millions of euros for this thing that had been around for 5 or 6 years because it was cool technology and we liked the team. But the CEO, who was already rich, wanted hundreds of millions of euros, and met with the CEO. He told the CEO, well, your entire business is going to explode in the next 3 years if you don't buy our company. And that's why I think we're worth probably at least $100 million or more, probably more. And the CEO said, that guy's such an arrogant jerk. I don't care how bad you think we need it. I'm not doing business with that guy. And that is when I learned don't get too greedy, I already learned don't be a jerk by this point, so don't be greedy was new for me. You know, I think that it's important. It sounds great to kind of always chase more dollars, but I can't tell you how many companies I've seen that think they're going to be 100 millionaires someday and they're not rich like this guy, and they walk away from tens of millions of euros, or even, you know, 3 to 5 million euros that would make a huge, meaningful impact to their life and to their family's life, and they walk away from it because they're unrealistic about where they're likely to end up, and they're also greedy. So you have to be focused on being more realistic and more greedy. Now, for the guy in question who was the CEO, it didn't matter. 3 or 4 years later, he sold it to one of our competitors, and by the way, and he made not as much as he wanted, but he still made plenty of money. But he had his biggest deal by far after that. He invested in another company where he was the biggest shareholder, which turned out to be King.com, the makers of Candy Crush. I'm sure that you have it. So he is now like a billionaire, and he owns his own football club, the Derby County Rams. So, you know, go Rams. Right. So the second thing I did at McAfee was really lead the drive on strategic initiatives. So the CTO kind of owned all that. And so what it really meant was I was doing mergers and acquisitions. I was going around talking to hundreds of companies a year, looking at those companies, figuring out if they might make sense for us to buy them. And I ended up doing 3 acquisitions that really I kind of drove the decision. Now, again, it's like mergers and acquisitions, a lot of people get involved. I was the first one in the door in the first 2 companies, and but again, I looked at hundreds and hundreds of companies and saw all the ways they went wrong. I'll tell you a little bit about each of the 3 of these. SiteAdvisor was testing the entire internet at the time, and when you Googled something, would put a red X or a green check mark next to each site. So they'd rewrite the page and annotate it and tell you if it was going to spam you, if it might have malware on it, if the ads were too obtrusive, whatever. It was great, and it was never going to make any money. And that was okay by me because antivirus is, everybody hates antivirus, and no one even thinks about antivirus until they have to pay more money for it because, you know, their subscription expired, or it missed something and they got infected anyway. So basically, they never see when we're doing a good job. They only see us when we're doing a bad job or we're asking them for money. So how are they going to like us? So for me, the thought was, let's give them something where, you know, we can show them every day as they're browsing the web that we're doing something good for them. And that definitely worked out pretty well. SiteAdvisor had hundreds of millions of users by the time that I ended up leaving McAfee. When we bought them, they probably had 1 million users at most. So absolutely huge. They never really made any money at all, which was okay. So, you know, really that was about building something at scale. Onigma was a technology company doing data loss prevention. MX Logic was doing cloud email. So, you know, the interesting thing about SiteAdvisor, though, is a great case study. They ended up having no revenue at all. How much do you think that would sell for in this day and age? I could probably have built their technology If I took my best people, it'd probably take me $3 million US and a year or so to build it. So, you know, we were thinking, okay, well, maybe we'll buy the company for $10 million and, you know, maybe we'd be willing to go up to 20. But then we found out that Symantec was bidding on the company as well, and the board of directors kept saying, I don't want to lose, I don't want to lose. Symantec had beaten them on their last big acquisition, they got it, and McAfee didn't, and they didn't want to be seen as weak. Well, that really sucks. So there are two lessons here. First is that most companies, 99% of companies have pretty weak teams that aren't good at executing. Most of the companies I looked at, even if they had a good idea, they were probably going to fail no matter what. And most of them were just kind of blindly copying what other people were doing most of the time. That's still kind of true. There are people that have there are teams that have one or two great people, but don't attract a great person in every role. So most companies have weaknesses. And you know, another lesson here is that the best companies that I saw tended to be funded by the best investors. So that means that the best people want to be funded by the best investors, and the best investors see the best deals and it's a circle of virtue if you're kind of in that world where the best investors want to put money into you and you want money from them. If you're anybody else, then you're immediately at a disadvantage. So it does pay to have pedigree is really what this means. So if you can kind of build the best team, if you can get the best investors, you should always strive to get the best of everything, because you're always selling something, even if it's the idea of your company or yourself as an employee. You're selling something, and you always want to look as great as possible. So find a good spin on it, but also it's why surrounding yourself with good people is so important. You want to be as well pedigreed as possible. And then, of course, you know, the third thing that I did was I was in charge of so I was the CTO for the software as a service business at McAfee, and which was a change in how we organized the company when the new CEO came in. And so like before, I had hundreds of people working on stuff, and it was combining all our cloud products, and I was supposed to go out and build new products on a platform, but I learned, especially with the new CEO coming in, that big companies have really big politics. It's not just that there are things, forces that are keeping you from getting stuff done. A lot of people are always trying to stab each other in the back, and I was good at avoiding it, but it really got tiring. I didn't really like trying to make someone's life miserable professionally and kind of take over their product, and that's what people were trying to do, and that happens everywhere, because going back to what I said earlier, most people are out for themselves before the company, and that's not great. It leads to politics. The guy who worked for me had probably 150 people 3 months after I left, because I was no longer there. Somebody kind of made a move on his organization, and he ended up with only 30 people before, 3 months later, and it kept getting chipped away, and he felt like a failure, and it was nothing to do with him. It was all because of stupid politics. And the politics is really why I ran out the door. I just kind of missed working at a small company, and yeah, at McAfee it was great. I could make a difference because I could build something that hundreds of millions of people were going to use, but yeah, that really wasn't providing enough satisfaction. I wanted to kind of make a difference in a different way. But a lot of good things came out of McAfee. I enjoyed the experience a lot. And one of the things that I learned is really how to be a good manager. And really, it goes back to what I said before. Put the company first when you're at work, and that includes the people that are working for you. So I think the most important tip that I can give you for managers is to really understand your employees, understand their goals, try to help them fulfill them. If it kind of makes their lives better and it makes the company's lives better, what's not to like? So really kind of respect your employees, try to help them grow, put them on par with the company, because that will come back to serve you. Again, I have lots of people that have worked for me many, many times, and it's because I'm convinced that I'm mainly always trying to look out for what they want out of their career and try to help them get it. The other thing is, McAfee was obviously, I had this big executive position. I was still really young when I got it. I had I was not qualified for the position when I walked in the door, except that I'd had this big failure with my first startup that was actually a huge impressive thing to the CTO of the company, because very few technologists have ever raised money from a venture capitalist, at least in that day and age. And he saw that I actually kind of understood a little bit about the business side of the world, and he trusted me enough to go in and talk to companies and learn about their financials and how they were managed. And that was all because of the failure that I had. And if that first company had been a success, I would have made more money from it, sure, but I would still have just been a technologist who worked on this one little problem, and that would have set me up to do something incrementally different the next time. McAfee gave me lots of opportunity to grow. I ended up making more than enough money at McAfee, and it led me to make more money in the future. So if you add up the economics, just because I had a company that wasn't a success, it actually was a huge, huge boost for my rocket and my career. All right, so that takes me to a company called Perimeter eSecurity. Now, this was 2010, and the name Perimeter eSecurity sounds like it should be out of 1992. And it was a horrible name. Its rocket was quickly plummeting to the ground and about to explode. It was actually a pretty well pedigreed company in that it was founded, it had Bessemer and Goldman Sachs as investors. I'm sure most people have heard of Goldman Sachs, but Bessemer is still one of the top handful of venture capitalists, top 5, and in kind of the software as a service world, they're like number 1 to 3, somewhere in that range. So they had this company that was absolutely a train wreck, but they thought they had some good technology, they had some crappy technology, they were not very profitable, and it was just a disaster. But they had some really big customers, United Airlines and Zurich Financial, kind of the U.S. division of that. So a lot. They were actually making about a little more than $50 million a year when I showed up. It's just that they really weren't making any profit, and they weren't growing at all, which was really, really bad for the investors. They had put a lot of money in, and the biggest challenge came from a company called Microsoft. So one of the things that this company, Perimeter eSecurity, was doing was selling hosted email. which Microsoft started doing with Office 365, and they did it a lot better than anyone else in the world was likely to do it, except maybe Google. And so the expectation was this business wasn't getting any better. It was only going to explode because everybody was going to leave and go to Microsoft. Well, suffice to say, United Airlines, Zurich, they did not end up going over to Microsoft. What I did was a couple things. First, we eventually updated the name, didn't look like we were in the 90s, tried to kind of put the past behind us and not have people remember how ugly the company used to be. But then we ended up, I really focused on what products can I build that I can leverage with this company. And so it was really, what can I deliver first to the customers that I have today that's going to solve new problems for them that they're going to find really valuable and is going to make us make them want to stay with us instead of going over to Microsoft. And it turned out that, of course, even though Microsoft was doing security, we could solve their security problems a lot better. So one of the many things we did, for instance, was what we call zero-day protection, which meant essentially protecting them from unknown exploitation, unknown attacks for things like email coming through their systems. And we did that really, really well and took a bunch of customers that weren't really happy and were thinking about going to Microsoft and made them very happy, loyal customers. Now, it's a much more complex story than that, but we ended up getting a lot of revenue based on our intellectual property. We started attracting new customers because of our intellectual property. We allowed new customers to buy it and buy Office 365. They didn't have to buy mailboxes from us. We didn't care. We kind of knew that business was going to go away, and the goal was to essentially change the tires on the car while the car was moving down the road. And we managed to do that really successfully. The kind of other stuff that we built there. But at the end of the day, we got acquired 4 years after I started for $250 million or so by BAE Systems, which is the British defense company. There were a lot of other companies that were very interested as well, and that was a tremendous win because, remember, the investors who'd pumped a lot of money into this company thought they were probably going to lose every cent, and then we ended up turning it into a huge success in a very short period of time. So one of the ways I did that is by not really worrying about the competition at all. You'll see this kind of chart a lot in your career. Lot of product companies kind of manage themselves this way. They're going to compare themselves to each other. So it's always the company on the left who published this. I know who they are, but no one's ever heard of them. It's a product called Semaphore, and they're talking about how they compete against Slack and against Microsoft. These things suck. So first, most companies in a competitive environment are going to focus on trying to make all the boxes green. No matter who they are, they're going to look at what other people do, and they're going to focus on trying to make that green. That's not what we did. We didn't say, we're going to do what Microsoft does. We're going to focus on like being the best mail hoster at all. Nope, we focused on what are the problems that they're not solving that are important to those customers, and can we solve them well? If we focused on the check boxes all day, we never would have built anything interesting. We would have just been me too, me too, me too, me too. And don't ever put one of these up to anybody because they don't really help. If I'm someone who likes your product, I don't need it, and it's possible that I'll learn about your competitors this way and then go off and research them. If I already dislike your product, I'm going to look at this and say, that's garbage. You're trying to make yourself look good, even though everybody knows that Slack and Microsoft are clearly better. Clearly they're better. Why are you trying to make it look like you're better than them? So it erodes trust. Nobody wants to do business with you. So I don't like this tool, but a lot of companies manage this way, and it's not the way we won. It's not a good way to win. So that's the lesson here. Don't focus on the competition's marketing. If you're gonna think about the competition, you want to focus on the problems that they're not solving that are important to your customers. And if you're not losing to them ever, then you shouldn't even worry about them. I mean, people ask me all the time, oh, how about so-and-so? They're a competitor, aren't they? Not until they win a single deal from me, and then maybe I'll think about what they're doing. Until then, I'm going to really focus on what customers want. So, acquired by BAE Systems, I ended up managing the teams that did a couple of other products. One for fraud analytics. This is all out of the Dedica acquisition that BAE Systems had done a long time ago. They were doing a lot of analytics, all professional services driven, but they had what they called products in fraud analytics that did very, very well. A lot of global banks liked those products, and then a security analytics product. So this is only 4 years ago. I'm going to briefly talk through both of those because I think it motivates what I was just talking about. I think when you're in a product world, the goal is to win, right? It's to have the biggest impact as possible, and that's going to give you, I think, the most career satisfaction. So if we look at how people focus their efforts on what they're going to build, some people focus on doing whatever it takes to acquire more and more customers, and some people focus on doing what it takes to make their customers happy. What tends to happen is if you only focus on making your customers happy, you end up with 1 or 2 customers that are very happy. But if you focus on acquiring customers and don't worry about making your existing customers happy, then you end up with a tire fire. And I will kind of explain that in the context of those 2 BAE businesses. So first, if you don't really do either, a lot of companies are like that. They're called technology-led companies. That means you build what you think is cool, what you want to build. And you don't worry about who wants to buy what. You build what you think people want to buy, and then when you're done, you run around and try to sell it. That almost never works out. However, it is what most people try to do when they're building a product company. The second is when you really focus on getting a lot of customers, but you really don't try to build to kind of to making all of your customers happy far into the future. And this is called deal-led. So the basic idea here is if you don't add features until some customer needs those features in order to close the deal, and you're on that treadmill forever. And so what ended up happening with their fraud analytics product was it had once been great and had taken over the world, and then they ended up focusing on kind of professional service-led deal acquisition, so they weren't building the things that customers really wanted. They were just customizing in order to win new business without kind of saying, well, what new problems should we be solving? And everybody was pretty despondent, and what ended up happening is they did so much customization, they did so many different versions that no one could keep up with them, and no customer could ever be upgraded without spending €1 million to upgrade, because it was that big and painful because of all the customization that comes from just focusing on getting new customers and not worrying about building the right thing that's going to make people happy. So that was the net reveal side. Now the security analytics product was customer-led. They basically were building a product for one customer. They wanted to make that customer really, really happy, and then they ended up getting to the point where they made 3 customers really, really happy. And to their credit, they were each deals that brought in over £1 million in revenue to the company, but they built something that no one else wanted, and they would have had to build essentially most of a new product for any new customer they got. So those 2 things are more or less failures. I think in a deal-led world, that's pretty traditional professional services organization. You build a platform and you can customize it for each customer, but it doesn't scale to the point where you can make a difference to everybody. What you want is to be market-led, meaning that you're building something that's going to help you acquire customers, but is also going to make both your existing and your future customers happy. And there is a trick to that. There's a trick to that, and I'll get to it in 1 minute. But first, the lessons. First, this organization that acquired us, make no mistake about it, they were a professional services organization. They wanted to become a product organization. That's why they acquired us. They could not easily change the professional services culture at a large company. I've seen it time and time again. Large professional services organizations are great at building technologies. It is almost impossible to be a professional services company and turn that into a product that scales. That doesn't mean it doesn't happen, but it is absolutely so rare as to not be worth mentioning. Okay, so I'm going to tell you about the rocket ship that I'm currently building, which is Capsulate. And kind of summarizing my entire career, we were able to get Capsulate funded. Most people, rightfully so, have to spend months and months, usually 6 to 12 months, to raise capital from venture capitalists, if they do at all. I had kind of such an experienced team walking in the door that previous investors who were my investors in Silver Sky were ready to fund us the moment we walked out the door, and so were several other investors. And it didn't really matter what we did. The lesson here is the reason why that's the case is because my entire career I've always been working hard to try to make myself great at something. And that something has to be both kind of hard as a skill to develop and important to people. And I first started out doing that with kind of just software engineering. I wanted to be a great software engineer. And then I wanted to be great at security. And then I wanted to be a great manager. And then I wanted to be great at business. And the fact that those things tend to be really hard, especially as you stack them up. Like very few great technologists become great business people. That makes the difference. That makes me more qualified for the job than most people, and it gives people a lot of confidence in my ability to do the job. And I'm not saying that to brag. I'm saying that because I think a lot of people say, I'm going to get really good at this one thing, and that will carry you to a certain point. But when you become the expert, don't rest on your laurels. Go become the expert in something else that's also hard and important. You'll still be enough of an expert in one area, but go off and broaden your own horizons. It will make you more valuable, especially if those things are not really closely related. So I think was an important insight for me. I didn't just want to focus on kind of code security forever, for instance. So Capsulate, in a nutshell, is doing zero-day protection, so protecting against unknown threats for people's production infrastructures. That means what they've got running in the cloud, like Amazon or Azure, or in their own data centers. And doing that at scale to hundreds of thousands of servers, making it easy to investigate and being able to detect problems in real time and respond to them is something that no one's really done. There's been a lot of focus on Windows. There's been a lot of focus on kind of doing deep analytics after the fact to see how you were hacked yesterday. There's nothing that is doing a good job of helping people prevent those attacks right now. So, we had enough experience with large-scale systems, hundreds of millions of users, that we could kind of build this and make it easy, but the secret wasn't actually, and we're about to release our first product, but we've got a lot of large enterprises, including a couple of European enterprises that are kicking the tires and saying great things about the product, even in public. And the reason that has nothing to do with my expertise at all. It is not a great product because of me or anybody on the team, not directly anyway. It's a great product because what we did was we walked around to over 40 large companies, all names that you all would have heard, and said, tell me what you're doing here. What are the problems that aren't being solved? What keeps you up at night in this arena? We found that they all had a lot of the same problems, and we said, well, how could we solve those problems for them? And so, we built a product, not a technology. So, I'm going to finish up with kind of the advice for how to build a rocket ship if you're doing products. First is build the best possible team. I kind of already talked about that. Second's the thing I'm really going to focus on for the rest of the talk. I've talked a lot about how it's important to be market-led. And yeah, at Capsulate, I went in and talked to 40-plus customers, and that really helped. But really, what does that mean? And the third thing is to just execute well. And what I mean by that is even if you do the first two right, there's still a lot of things that can trip you up. And the reality is, even if you've got the best possible team, there's still a pretty good chance that you can fail outright, be a miserable, abject failure. Okay, so finally, how to be market-led. This is where the magic happens. I'm going to start by asking you a question. You see this refrigerator? It's got a TV in it. How would you sell this product to somebody? You want your parents, your salesperson, it's your parents. Do you think you can convince your parents to buy this refrigerator? Does anyone think they could sell this refrigerator? Probably not, right? Why? No one needs a TV in the refrigerator. Like, what are you going to do with it? Are you going to, watch Netflix on your refrigerator? Really? No one wants to pay money for that. Nonetheless, people spend a lot of money to develop these refrigerators with TVs in it. What were they thinking? And interestingly enough, if you go into a store, people might want to ask a lot of questions about it because it's interesting. It's kind of cool that there's a TV in the refrigerator, even though I would never in a million years want one. And so people might have thought that we wanted to buy a TV in a refrigerator because they went around and said, you think TV in a refrigerator is interesting? Oh, yeah, cool. What could you do with it? Oh, yeah. But it doesn't really solve any problem that they have, right? So no one's going to buy it unless you're basically doing it for free. So a lot of products, most products are kind of built this way. All the decisions get made within your team based on knowledge you have, and then those decisions get pushed out to the rest of the world. You say, here's our product, and you say, here's our marketing. This is what we call inside-out thinking. You're starting with you, and you're kind of then pushing out to the rest of the world. That doesn't really work very well. Instead, the goal is to get as much information from the outside world into the company and use that as the basis of your decision making, and that's called outside-in thinking. Okay, now, I'm going to give you a quiz here. Why do people buy products? Look at this office. Imagine you're getting hired into this office. those dividers are kind of rare these days now. It's just kind of like low desks. And so imagine your desk is right here, and you have to listen to all of these noisy people all the time. What product are you suddenly in the market for? What are you going to go out and buy because of this? Headphones, right. So why did you buy that product? Why do you buy most products? Most people buy products because they solve problems that they have. They want it, sure, but they want it because it does something meaningful that makes their life better, and often it's solving a problem they have. And so the trick is not just realizing that your job is to find those problems. You need to be able to differentiate between kinds of problems. Like looking at a recipe on a refrigerator might make it a little bit easier to like make your dessert tonight, but that's a minor problem. It's what I call a paper cut problem. It's not that big a deal, as opposed to a gunshot wound problem where you will pay absolutely every cent that you have and will ever make for a solution to that problem, right? So the goal is essentially not just to find problems, but to focus in on the big gunshot wound problems. And 4 quick ways to maximize success. First is building the right thing, solve important problems, stay focused, meaning address the most important problems first. In the software world, we tend to build things with lots and lots and lots of features. People usually don't want that. They just want solutions to problems. Solve one problem first, the most important one, and then you can solve all the little problems around it. But then it behooves you to get good at showing people why you solve their problem instead of trying to like make it use a lot of jargon and sell things kind of by spending a lot on advertising. Talk to people about their problems and show them that you're passionate about solving those problems. And then another important thing is that you really have to focus on not creating new problems when you're trying to solve a different problem, which often happens. And so the guideline there is remove friction. So that often means, well, your product now makes it, gives me something I have to go off and install and have to maintain. And well, can you automate any of that? Because that will help. Oh, well, you know, I love your product. It seems really interesting, but it's actually now causes me a bunch of new problems because I have to actually buy it, and I'm at a big company, and that's a long 6-month process. Well, what can I do to remove friction from that, make it easier? Those are the things that you really should be thinking about. And so the secret that I promised you, the things that almost no company does today, almost no product company, is focusing on going outside the organization, bringing that information in, focusing on important problems, and using that as their strategy for going off and executing. When we started Capsule 8, we had a rough idea that we wanted to help people with production infrastructure security because we knew it wasn't being done well, but we really weren't, had no idea what we would actually build until we listened to all those people talking about those problems, and then some of them told us what they thought they wanted, but listen to their problems, don't listen to what they think the solution is. That's a very consulting thing to do, and it doesn't scale. Focus on understanding the problems in a lot of different environments, and then you bring the expertise to find one solution that will work for lots and lots of people in one market. And so that is the core secret, the one thing that I'd say that 99+% of startups don't do that would definitely make them a lot more successful. Now, there's a lot more to product execution. We really have only covered the first 2 rectangles there, And there are plenty of ways that that rocket can explode, of course. So even if you're passionate about something and want to go off and solve the problem, I'm not saying that this is going to definitely make you successful. It is really, 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 really hard, but it is very rewarding. And whatever your goals are, whether it's going out and building your own product company, I just would absolutely encourage you to go after your goals as intelligently as possible. Kind of keep these lessons in mind, because in the words of a famous Canadian sports star who is not a football player, sorry, you miss 100% of the shots that you don't take. So if you've got big, audacious goals, go after them. Don't kind of sit there and watch life pass you by. Thanks a lot. Sure. Do we have time for questions? Yeah, a couple minutes. Any questions?
So at the beginning of the lecture, you told us that your goal was to make a difference in the world. So would you say that you have accomplished that?
I always want to be making more of a difference, but I guess that my entire career, I've always set new short-term goals and kind of readjust, like my long-term goals. And I feel like I've always overachieved, often by dumb luck and by the fortune of just kind of benefiting from others. And so the answer is yeah, I definitely feel like I have. So for instance, kind of encryption that runs pretty much universally everywhere, having hundreds of millions of people using software those things are all really rewarding, but I always want to do more, and that's why I do still try to, when I can, teach at NYU, why I like to do things like this. I just like to give back. The guy who wrote an article about how bad of an employee I was cares a lot about giving back, and gave me a lot of opportunity, and I've followed in his lead. And a bunch of other great computer scientists. When I first got to college, one of the most famous early computer scientists, Bill Wolfe, gave a really motivating speech saying essentially that if you ever become successful, then you benefited from kind of this great community that you really need to give back to. Otherwise, you're just being selfish.
Okay. Thank you. Anyone has another question? Probably the last opportunity you'll have to make a question to John Viega. So
I know everybody wants to go eat, but I'm happy to talk about anything. I can talk about tech, I can talk about business, whatever you want.
Okay, fine. I'll go there, don't worry.
Yeah, during your presentation, you talked about professional service and product companies. What did you mean by that? I didn't really get that.
Yeah, so it's interesting because from what I've seen, most of you will go off into professional services organizations. In a nutshell, the goal when you're building a product is to build something where, without changing it, without a lot of work, many people can all use the same thing. Professional services, you are kind of like a waiter or waitress in a restaurant taking a custom order and building exactly what that person wants. Often it's not entirely building software, it's advising and so on. In a product world, we tend to try to never do that. We want to scale ourselves by building something that as many people as possible can consume as easily as possible and as repeatably as possible. Ideally, they call it kind of a cookie cutter. You want everybody to be able to get the same thing very easily with very little effort. There's nothing wrong with professional services at all. It is very tough to have an impact across more than a handful of organizations in your career if you go the professional services route. You know, the customers you have, you might do something great for them, but if like it was to me, it was important to feel like I was making a big difference to lots of people in lots of different places. I never would have been able to do that if I'd continued to do professional services, because they are, as we call it, like N=1 activities, whereas building products are for the many, so N=many, right? So that's really kind of the difference.
Okay, thank you. So if anyone, oh, okay, then.
Hi there. Why would you say that the market-led type of business or company is the goal you want to achieve in your company?
Well, it is not the goal in and of itself. The goal is to make a difference to as many people as possible by the work that I do. And one of the best ways to scale that is by building products that a lot of people are going to want. And I think is true because if you don't take that approach, then it's very hard. You can luck into it, but it's very hard to build something that a lot of people are going to want to buy. It really, or even use. So I've done open source software and have gotten lots of adoption on that. It's all the same to me. If you treat it like building something custom, then you're going to get a kind of a fraction of the potential customers or users.
Then would you say that in different stages of the company's growth, you would opt different strategies in terms of the goal you want to achieve? Like, would you say that in the beginning you would go for a deal-led? No, I mean, always market-led?
Look, I think that if you can afford not to, then don't. One of my early lessons was essentially that it's tough to do one thing and also build a product. So, and I've got friends that I've put money into their companies that are doing exactly this now. They're trying to build out a product while also doing professional services, and it's very distracting. So you have to keep your customers happy. You end up never doing a good job building the product or learning about the people that should be your customers. The basic idea of going out there and learning is to try to create as many potential buyers as possible by filling in your ignorance from your little perch kind of over in your corner. I definitely have lots of opinions on things, but as someone who builds products, I think those opinions are irrelevant unless I've heard them from the outside and have a lot of outside evidence that, because I'm always looking to scale what we're doing, if that makes sense.
Okay, thank you.
Yeah. But I'm going to say a couple more words on that. If you had to, I mean, I think that if you're cash-strapped, people do it, and the question is making the transition becomes tough. It's also, if you do want to be one of the people swimming in a big bathtub of money at some point in your career, products are a lot more valuable than services to potential acquirers. If you've got a successful product, it's worth a lot more. That's where the big dollars come from, because you've built something they can scale as well, because they're also trying to make more money, right? So that's why, in a nutshell, no matter what your goals, you probably want to have a big impact, whether it's because you want to make a lot of money, you kind of genuinely want to make a difference in the world, or you want to feed your ego and make a difference in the world. It's all the same. You want to try to maximize the impact that you have, and that gives you the best success, odds of success for doing it.
So are there any other questions?
Hello. So you said that oftentimes the best products don't win.
Oh yeah.
So I mean,
I said the best technologies
yeah,
don't
okay.
always win.
The best technology. Then,
yeah.
If let's imagine I'm trying to create some technology that's already well established in the market. How would I go about winning against companies, even if my technology might be better, since they're far more well known?
Yeah.
I might not have a chance. How would I go about advertising my product and showing people that
Yeah.
it is actually superior?
So first of all, if you can do something better than me, but I was already solving the problem well enough, you're not solving any new problems, you're not providing incremental value, and just because you can say, well, you know, my new, like I did this with a different machine learning algorithm, and so you get like 2% fewer false positives. That is demonstrably better technology if you can prove it out, and probably no one will ever care because they want everything else too. And a great product understands the buyer and how they buy and how they use the product in great detail beyond just the technology. It's about the installation, it's about the ease of use, it's about all the little things, and it's about the sales and marketing. So just kind of understanding how easy it's going to be to kind of buy the product. Startups tend to die and go away, and then you're using this product that even if it's the best product in the world, maybe it breaks and no one's around to support it. So it's really tough to do well by copying what other people are doing and trying to do it a little bit better. It's a lot easier, even though it is still really, really hard, to go in and kind of find a market of people that all have a problem that isn't really being serviced very well, that's a gunshot wound problem. It's an important problem to them. And if you do that, then you'll be able to sell a vision that will get qualified people interested in working with you, because you know you're onto something. You know you can parade around people who say, yes, I have this problem. And so the unfortunate thing is, to kind of get back to your question, is a lot of it is relationships. You need to be able to get in front of people that can spend money, that know what their problems are, that are willing to spend time to talk with you about them. You need to be able to attract people that are good at like the sales and marketing, because those things are important too. You could build a great product but not know how to actually get it out there. Nobody knows it exists and you still go under. All of those things definitely happen. So I think that focusing on kind of building your professional network, but more than just kind of adding a lot of people to it, build quality relationships where kind of you understand each other's strengths, and kind of I think those, if you build friendships in those circles, it'll serve you very well to kind of eventually being able to break in situations where you do have something interesting that people would buy, but you've never done it before. Does that help?
Yeah, it does. Thank you.
Good. Yeah.
Anyone else?
When did you realize that you wanted to go with this field? I mean, you said you wanted to make a difference.
Yeah.
Why cybersecurity?
That was, like I said on the slide, it was dumb luck. So in computers, in a sense, was dumb luck too. That's why I didn't get started until college. I kind of always wanted to be a writer, and I saw myself as kind of like a fiction writer, and I saw in college somebody playing an online text adventure with other people interactively, and I thought, well, they've made that into a game, but I could make that into a really interesting piece of fiction that involved a lot of people if only I knew how to do that. And so I really was motivated to teach myself how to program because I wanted to be able to write stuff like that, mainly because it was wrapped up in who I thought I was. It was my ego that I wanted to be a writer, and you know, but then I kind of started realizing I'm actually getting really good at programming, and maybe that, and I'm enjoying it, and so maybe I should be thinking about doing something different. But I still like leapt at the chance to write a book, even though it wasn't fiction when I got it, and I kind of it's not anybody's idea of fun. So with security, I wanted to do academic research coming out of college, and I wanted to stay close to home, and I liked the people. That they were very smart, they were very motivated as well. The fact that they were doing security, I didn't really care about that. And to this day, I'm really good at security, and I'm probably one of the least paranoid people in security. I really don't have the same kind of fear that a lot of security people have. So.
Thank you.
Yeah, thanks.
No one else has a question?
Hey, it's me again.
How you been? It's been a while.
Yeah, I'm okay. Good. I was wondering, what do you do in your daily life?
Like when I'm not working?
No, when you're working.
It's something different every day, and that's really good for me. I'm not great at doing the same thing every day. I get very bored. Not everybody does, and I think it's important to kind of recognize your weaknesses and kind of play up to that. So I'm lucky that I'm in a role where something's different every day. So it could be, even in this company, I have been hiring, I've been kind of selling the company. Mainly what that means is kind of getting the next round of money to come into the company, because most startups for years need money to grow fast, just a rocket ship. So that always requires one of my key responsibilities to be going out and finding new investors, communicating to the investors, helping the teams do their job. If something falls down, then I go in and help fix it. When we're out selling the product, I'm often talking to them, listening to what they want, bringing that back in so we can kind of prioritize it against everything else. So it's something different every day, which is one of the things that makes it such a great job for me. Yeah, I've even written some code in this product, believe it or not. Tiny bit. It's dead. Yeah, I can hear you. Go ahead. Hmm. Yeah, it's not that I wanted to know what their actual flaws are, meaning how I could break into their environment. I want to. Yeah. Really, most people are fairly trusting most of the time. They're good people that want to help other people. And even early in my career, before I had a large network with a lot of relationships, if I get an introduction to somebody, or even just reach out to them on LinkedIn and say, you know, I really am not trying to sell you anything. I just want to learn from you. Could I get 30 minutes of your time to hear you tell me about how you think about whether you have these problems and how you think about it? That'd be really valuable to me, and most people, especially if you've got any kind of introduction at all from anybody they know, is a lot of people will say yes to that question. And so even in security, nobody pretends that they're perfect. That's just not realistic. The entire industry knows it. So it's no problem for somebody to come in and say, these are the things that would make our organization more efficient, that whether that means kind of less time getting hacked and cleaning up, or less work and cost to kind of defend. People are willing to discuss those things. They're not willing to put kind of make their companies look bad, but I'm not asking them to, and I'm also not sharing any of that information about what they said to anybody. And so that's pretty typical. You know, a lot of companies are willing to do that if you ask them. Does that help? Does it surprise you? Yeah. Would you help me out if I wanted to learn? Maybe. Maybe like I give you a Starbucks gift card if you help me out. That actually giving somebody $20 just for them doing you a favor will lead to even more yeses. So you know, if they feel like it's personal as opposed to kind of fill out this checklist somewhere for me, please, nobody will do that. But if we're going to have a real human connection and I feel like I'm helping you, I'm more inclined to do that even if I have no idea who you are.
So thank you very much for being here today. It means a lot to JEEC, and I'm sure I speak for all of us that we had a lot to learn from you, and it was a great lecture, so thank you for being here. So let's... Thank you so much. So we're gonna end up the prize. Yeah.
This is for me.
We're gonna do like a...
These are nice Beats headphones.
So
the winning number is 4.
Oh, there you go. So come here.
You're all jealous, aren't you?
Well, this is 4.
That is 4. Here's your prize.
Thanks.
Yeah.
It's been a pleasure.
Thanks.
Okay, thank you for being here. And
have a good evening.
Exactly. It was incredible, really. Like,
No,
I didn't have to pinch you.
I was only joking. I mean,
I'm gonna hand off the microphone.